If you like the space and learn about its curiosities, consider subscribing to the channel. We have 2 videos every week. Thank you for your attention and enjoy the video. In the vastness of the cosmos, the universe has always been a source of fascination and mystery. Every time we look up at the night sky, we're reminded of how small and insignificant we are compared to the infinite expanse stretching out before us. It's a place where time bends, where the laws of physics take on forms that defy our earthly understanding, and where every star, planet, and distant galaxy holds secrets yet to be discovered. Our journey today will delve into the most intriguing and mind-boggling curiosities that space has to offer, from the mysterious dark matter to the furthest reaches of the observable universe. Space, as we know it, begins at the Kármán line, roughly 100 kilometers above Earth's surface. At this boundary, the atmosphere becomes too thin for conventional aircraft to fly, and space officially begins. But the journey upward doesn't end there. This is just the starting point. As you move beyond, the first thing that strikes you is the sheer silence. Without air to carry sound, space is eerily quiet. No footsteps, no engine hums, not even the crackle of radio static unless we artificially introduce it. It's a place of complete stillness, except for the constant motion of celestial bodies. One of the first major mysteries of space is the concept of dark matter and dark energy. Although they make up about 95% of the universe, we can't see or detect them directly. Dark matter is thought to be the scaffolding that holds galaxies together, providing the gravitational glue that allows stars to orbit their centers without flying apart. Without dark matter, galaxies would disintegrate. Dark energy, on the other hand, is even more puzzling. It's responsible for the accelerated expansion of the universe, pushing galaxies apart at speeds faster than we would expect from the observable matter alone. The discovery of this cosmic force has led scientists to rethink the future of the universe, speculating whether it will expand forever, reach a breaking point, or collapse back in on itself. Moving closer to home, the moon has always been Earth's silent companion. Yet, there's something quite strange about it. For starters, it's too big for a planet the size of Earth to have captured it naturally. Many scientists believe the moon formed after a Mars-sized body collided with Earth, spewing debris that eventually coalesced into the moon. Another curiosity lies in the fact that we always see the same side of the moon, a phenomenon known as tidal locking. As the moon rotates, it does so at the same rate that it orbits Earth, ensuring that only one hemisphere is visible from our planet. The far side of the moon, often mistakenly called the dark side, isn't perpetually dark. It gets as much sunlight as the near side but is never visible from Earth. And what about black holes? These cosmic phenomena have captivated both scientists and science fiction writers alike for decades. At their heart is a point of infinite density, known as a singularity, where the laws of physics as we understand them completely break down. Surrounding this singularity is the event horizon, the point beyond which nothing, not even light, can escape. This creates a boundary that, from an outside perspective, seems to freeze objects in time as they approach it. The intense gravitational pull of black holes distorts time and space, creating a phenomenon known as gravitational time dilation, where time appears to slow down near a black hole relative to an observer far away. If you were to approach the event horizon, time for you would seem normal, but to an outside observer, you'd appear to be moving in slow motion, eventually freezing as you cross the boundary. Then, there's the question of the multiverse, an idea that is as mind-bending as it is controversial. The multiverse theory suggests that our universe is just one of many, perhaps even an infinite number, of parallel universes. Each of these universes could have different laws of physics, different forms of matter, and even different versions of ourselves. The concept arises from the idea that, at the quantum level, particles can exist in multiple states at once. If this holds true for particles, it could also hold true for entire universes, creating a vast web of alternate realities. While there's no direct evidence for the multiverse, some physicists believe that the existence of other universes could explain certain phenomena, like the finely tuned constants of our own universe that allow life to exist. As we move further out into the universe, we encounter other bizarre phenomena, such as neutron stars. These are the remnants of massive stars that have exploded in supernovae. What's left behind is a core so dense that a single sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. These stars spin incredibly fast, with some rotating hundreds of times per second, emitting powerful beams of radiation in the process. This makes them appear to pulse, earning them the nickname pulsars. If you were to stand on the surface of a neutron star, though it's impossible given the crushing gravity, you would experience gravity millions of times stronger than on Earth. Let's not forget about exoplanets, planets that orbit stars outside our solar system. With the discovery of thousands of exoplanets in recent years, scientists have begun to speculate about the possibility of life beyond Earth. Some exoplanets exist in the so-called Goldilocks zone of their star, an area where conditions might be just right for liquid water to exist, and therefore for life to potentially thrive. One of the most intriguing candidates is Proxima b, an Earth-sized planet orbiting the closest star to our Sun, Proxima Centauri. Proxima b is located within the habitable zone, but whether it has an atmosphere or the right conditions for life remains unknown. Even more fascinating is the idea of rogue planets, planets that don't orbit any star at all. These lonely worlds drift through the galaxy untethered, heated only by their own internal processes or, possibly, the faint light of distant stars they pass by. Some estimates suggest there could be billions of these rogue planets in our galaxy alone, wandering aimlessly through space, invisible unless they pass in front of a distant star and cause a temporary dip in its light. As we think about the future of space exploration, one of the most exciting developments is the possibility of humans becoming an interplanetary species. Mars, with its dry, rocky surface and thin atmosphere, has long been considered the most viable option for colonization. NASA and private companies like SpaceX are working on plans to send humans to Mars within the next few decades, with the hope of establishing a permanent colony. The challenges are immense, from the psychological toll of isolation to the practical difficulties of creating a self-sustaining habitat. But the potential rewards are equally vast. A successful colony on Mars could serve as a stepping stone for further exploration of the outer solar system and beyond. In addition to colonizing other planets, scientists are also looking into the possibility of asteroid mining. Asteroids contain vast amounts of valuable minerals and metals, including gold, platinum, and rare earth elements that are critical for modern technology. Some estimates suggest that a single asteroid could contain more resources than have been mined in all of human history. The idea of harvesting these resources from space isn't just science fiction. Several companies are already working on the technology needed to mine asteroids and bring their riches back to Earth. Finally, one of the most awe-inspiring curiosities of space is the phenomenon of cosmic time. When we look at distant stars and galaxies, we're not seeing them as they are today, but as they were millions or even billions of years ago. This is because light takes time to travel across the vast distances of space. In a sense, telescopes are like time machines, allowing us to peer into the distant past of the universe. The further we look, the older the light, and the closer we come to seeing the birth of the universe itself, in the form of the cosmic microwave background, faint radiation left over from the Big Bang. These are just a few of the many wonders that the universe holds. From the mind-bending effects of black holes to the possibility of life on distant planets, space is full of mysteries that challenge our understanding of reality. As we continue to explore and learn, one thing is certain: the universe will always keep us guessing, and each new discovery will only deepen our sense of wonder. As we continue to gaze into the night sky, our journey through the mysteries of space is far from over. The deeper we look, the more we realize how little we know. Take, for instance, the concept of wormholes. These theoretical passages through space-time are often depicted as shortcuts across vast distances in the universe, connecting 2 points in space, as if folding a piece of paper and punching a hole through it. Wormholes, in theory, could allow for near-instantaneous travel between distant galaxies. While none have been discovered, the possibility that they might exist has fueled countless theories and inspired much of our modern science fiction. If wormholes do exist, they could offer solutions to the problem of interstellar travel, something that would otherwise take thousands, if not millions, of years using conventional propulsion. Wormholes aren't the only strange anomaly in space, though. Let's talk about quasars, one of the brightest and most energetic objects in the universe. Powered by supermassive black holes at the centers of distant galaxies, quasars emit extraordinary amounts of energy as matter spirals into the black hole, generating light that can outshine entire galaxies. What makes quasars so fascinating is that we can see them from billions of light years away, meaning we're looking at some of the earliest galaxies to form in the universe. The light from these quasars has taken so long to reach us that it offers a glimpse into the universe, as it was just a few 100 million years after the Big Bang. Speaking of the Big Bang, one of the most profound questions in cosmology is what came before it. The Big Bang theory suggests that the universe began as an incredibly hot, dense point and has been expanding ever since. However, what preceded this moment of creation remains one of the greatest mysteries in science. Some theories propose that the universe underwent a cycle of expansion and contraction, with a big crunch occurring before the Big Bang, resetting the cosmic clock. Others speculate that our universe could be one of many in a larger multiverse, with each universe undergoing its own Big Bang. While we may never know for certain what existed before our universe, the question continues to spark debates and drive research in theoretical physics. Another enigma that defies understanding is the Fermi paradox. Named after the physicist Enrico Fermi, it highlights the contradiction between the high probability of extraterrestrial civilizations existing in the universe and the complete lack of evidence for or contact with them. Given the vast number of stars in the galaxy, many of which have planets in the habitable zone, it seems statistically likely that intelligent life should have arisen elsewhere. So where are they? Some explanations suggest that advanced civilizations may be avoiding us, or perhaps they've self-destructed through technological catastrophes. Others speculate that intelligent life might be so different from us that we simply don't recognize it when we see it. The paradox remains unresolved, but with each passing year, our search for extraterrestrial life becomes more sophisticated, increasing the chances of finding an answer. In our own solar system, one of the most puzzling phenomena is the strange nature of Saturn's moon, Titan. Titan is the only moon in the solar system with a dense atmosphere, and it also has lakes and rivers, but not of water. Instead, these lakes are filled with liquid methane and ethane, creating an alien landscape unlike anything found on Earth. Titan's atmosphere is so thick that you could theoretically fly by flapping artificial wings, and its surface may even harbor the building blocks of life in a form we've never seen before. Scientists are particularly intrigued by the potential for life to exist in such a cold, methane-rich environment, a scenario that challenges our understanding of what life requires to survive. Speaking of strange moons, let's not forget about Europa, one of Jupiter's largest moons. Europa's surface is a thick layer of ice, but beneath that icy shell lies a global ocean, potentially containing more water than all of Earth's oceans combined. This ocean remains liquid due to the gravitational forces exerted by Jupiter, which create tidal heating that keeps the water from freezing solid. Europa's ocean is considered one of the most promising places to search for extraterrestrial life within our solar system, and future missions aim to drill through the ice to explore this hidden world. Beyond moons, the study of asteroids has also revealed some truly fascinating facts. One such asteroid, Bennu, has drawn particular interest because of its proximity to Earth and its potential to impact our planet in the future. Bennu is classified as a potentially hazardous asteroid, meaning its orbit brings it close enough to Earth that there's a slim chance it could collide with us in the distant future. However, Bennu is also rich in organic materials and water-bearing minerals, making it a time capsule from the early solar system. In 2020, NASA's OSIRIS-RX mission successfully collected samples from Bennu's surface, which are now being analyzed to learn more about the building blocks of planets and life. Another interesting aspect of space exploration is the discovery of super-Earths, a class of exoplanets that are larger than Earth, but smaller than Neptune. These planets could have conditions conducive to life, with some potentially possessing thick atmospheres and liquid water. One such planet, called Gliese 581d, orbits a red dwarf star about 20 light-years away. It resides in its star's habitable zone and may have a rocky surface with oceans and an atmosphere thick enough to support life. Super-Earths are particularly interesting because they suggest that Earth-sized planets might not be the most common habitable worlds in the galaxy. Instead, planets with different compositions and atmospheric conditions could be the norm. When we look at our own star, the Sun, we see another cosmic curiosity. While the Sun appears stable and unchanging on human timescales, it is constantly undergoing violent eruptions known as solar flares. These flares release massive amounts of energy and charged particles into space, sometimes interacting with Earth's magnetic field to create the beautiful auroras. However, a powerful enough solar flare could potentially disrupt satellite communications, power grids, and even internet infrastructure, highlighting our vulnerability to the Sun's volatile nature. Yet, despite the Sun's ferocity, it is just one of billions of stars in the Milky Way, many of which are much more extreme. Take, for example, neutron stars, which are the collapsed remnants of massive stars that have gone supernova. These stars are so dense that a single teaspoon of neutron star material would weigh billions of tons. Some neutron stars are even more extreme, known as magnetars. Magnetars have magnetic fields 1 trillion times stronger than Earth's, and when they experience starquakes, the resulting energy can be detected across vast distances in space. These starquakes release gamma-ray bursts, which are some of the most powerful explosions in the universe, capable of outshining entire galaxies for brief periods. Lastly, we cannot discuss the wonders of space without mentioning the cosmic microwave background radiation, CMB. The CMB is the afterglow of the Big Bang, a faint signal that permeates the entire universe. By studying this radiation, scientists have been able to piece together a picture of the universe's infancy, only 380,000 years after the Big Bang. The CMB provides crucial evidence for the Big Bang theory and has helped us understand how the universe has evolved over billions of years. What's even more remarkable is that tiny fluctuations in this radiation reveal the seeds of all the structure we see in the universe today, from galaxies to clusters of galaxies. The more we learn about space, the more we realize how much we have yet to discover. From the hidden oceans of distant moons to the possibility of wormholes and parallel universes, the cosmos is full of mysteries that challenge our understanding of physics, time, and even reality itself. As our technology improves and our reach extends further into the stars, we stand on the cusp of answers that could reshape our view of the universe forever. Yet, with each answer will come new questions, ensuring that the exploration of space will never truly end. As we journey deeper into the cosmos, we come across even more perplexing and awe-inspiring phenomena. One of these is the concept of cosmic inflation, an idea that revolutionized our understanding of the early universe. Right after the Big Bang, the universe underwent an unimaginably rapid expansion, growing from subatomic sizes to macroscopic scales in less than a fraction of a second. This sudden inflation explains why the universe appears so uniform on a large scale, with galaxies and cosmic structures spread out evenly across vast distances. It also helps to account for the flatness of space-time. Without inflation, the universe would likely look much more chaotic, with matter and energy unevenly distributed. Though this theory is widely accepted, the precise mechanism behind inflation remains one of the biggest unsolved mysteries in cosmology. Another enigma that has baffled scientists for decades is the question of where all the antimatter in the universe has gone. According to the standard model of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. When matter and antimatter come into contact, they annihilate each other in a burst of energy, so the universe as we know it shouldn't exist. Yet, for some reason, there is far more matter than antimatter, allowing stars, planets, and galaxies to form. This imbalance is known as the baryon asymmetry problem, and solving it could unlock fundamental truths about the nature of the universe. Some physicists speculate that certain conditions in the early universe favored matter over antimatter, but as of now, the mystery remains unsolved. While we ponder the origins of the universe, we can also look at the extremes of what space has to offer, such as the largest structures known to exist, galactic superclusters. These are enormous groupings of galaxies bound together by gravity, forming vast cosmic webs that stretch across hundreds of millions of light years. Our own Milky Way is part of a supercluster known as the Laniakea supercluster, which contains over 100,000 galaxies. Yet, even these immense structures are dwarfed by the voids between them, vast regions of space where galaxies are sparse or entirely absent. These voids, some stretching hundreds of millions of light years, give the universe a honeycomb-like structure when viewed on the largest scales. Closer to home, there's the peculiar case of our own star, the Sun, and its ultimate fate. While it still has about 5 billion years left in its life cycle, the Sun will eventually run out of nuclear fuel and begin to die. First, it will expand into a red giant, possibly engulfing Mercury, Venus, and even Earth in the process. After shedding its outer layers, the Sun will leave behind a dense core, a white dwarf. This remnant will cool and fade over billions of years, turning into a cold, dark object known as a black dwarf. This transformation is a reminder that even stars, the cosmic engines of life and light, are not eternal. They live, evolve, and eventually die, leaving behind the building blocks for future generations of stars and planets. Among the more curious recent discoveries is the phenomenon of fast radio bursts, FRBs. These are incredibly brief but powerful bursts of radio waves that last only milliseconds, yet release more energy in that short time than the Sun does in an entire year. The origin of FRBs remains a mystery, but they are detected coming from distant galaxies, which suggests they are produced by some of the most extreme astrophysical processes. Some scientists speculate that they could be caused by neutron stars or black holes, while others propose more exotic explanations, including the possibility that they might be signals from advanced extraterrestrial civilizations. Though this idea remains speculative, the mysterious nature of FRBs has captured the imagination of scientists and the public alike. As we continue to push the boundaries of space exploration, we come to the idea of Dyson spheres, a hypothetical megastructure that an advanced civilization might build around a star to harness its energy. First proposed by physicist Freeman Dyson in 1960, the concept involves surrounding a star with a massive array of solar panels or other energy-collecting devices to capture every bit of energy it emits. Such a structure would provide virtually limitless energy for a civilization, potentially allowing it to expand across the galaxy. While no Dyson spheres have been discovered, the search for them has become a part of the hunt for extraterrestrial intelligence. Some scientists are looking for stars that appear to dim in irregular patterns, which could indicate the presence of such a structure. Back on Earth, we are not immune to the cosmic influences that shape the universe. One such influence is the potential impact of a gamma-ray burst GRB hitting our planet. Gamma-ray bursts are the most energetic events in the universe, believed to result from the collapse of massive stars or the merging of neutron stars. If a GRB were to occur close enough to Earth, it could have catastrophic effects, stripping away the ozone layer and exposing the surface to deadly radiation. While the odds of such an event happening are extremely low, they remind us of the unpredictable and sometimes violent nature of the cosmos. On the brighter side, the study of gravitational waves has opened up an entirely new way of observing the universe. First detected in 2015 by the LIGO Observatory, gravitational waves are ripples in space-time caused by cataclysmic events like the merging of black holes or neutron stars. These waves travel through the fabric of space-time, carrying with them information about their origins. Gravitational wave astronomy allows us to hear the universe in a way we never could before, providing new insights into the behavior of black holes, neutron stars, and even the early universe itself. When we look at the future of space exploration, one of the most tantalizing possibilities is the discovery of life beyond Earth. While we've yet to find definitive proof of extraterrestrial life, our search is far from over. Scientists are particularly excited about the potential for life on moons like Enceladus and Europa, both of which have subsurface oceans beneath their icy crusts. These oceans are kept warm by tidal heating, creating environments where life could potentially exist, even in the absence of sunlight. Missions like NASA's Europa Clipper, set to launch in the 2020s, will probe the icy surface of Europa, searching for signs of life in the water below. The discovery of life, even microbial, would have profound implications for our understanding of biology and the uniqueness of Earth. It would raise the question of whether life is common throughout the universe or whether it is an incredibly rare phenomenon. Either way, the discovery would fundamentally alter our place in the cosmos, forcing us to reconsider what it means to be alive in a universe that may be teeming with life forms that are entirely different from anything we know. Another frontier in space exploration is the possibility of sending probes to other star systems. The idea of interstellar travel, once confined to the realm of science fiction, is starting to gain traction with concepts like Breakthrough Starshot. This initiative aims to send tiny, light-powered spacecraft to our nearest stellar neighbor, Proxima Centauri, within a generation. Using powerful lasers to propel these nanocrafts to a significant fraction of the speed of light, the hope is that they could reach the star system in just a few decades. If successful, this mission could mark the beginning of a new era in human exploration, allowing us to explore other star systems and potentially find habitable planets or extraterrestrial life. The more we learn about the universe, the more we realize how interconnected everything is. From the smallest subatomic particles to the largest superclusters of galaxies, the cosmos operates on principles that govern everything from the formation of stars to the behavior of black holes. Yet, for all our progress, we are still only scratching the surface of what there is to know. Every discovery opens up new questions, and each mystery solved reveals even deeper puzzles. This endless quest for knowledge drives us to keep exploring, to keep looking up at the stars, and to keep wondering what lies beyond the next horizon. The wonders of space are a testament to the boundless creativity of the universe itself. From the strange and exotic forms of matter to the incomprehensible distances between galaxies, space continues to challenge our understanding and stretch the limits of our imagination. The more we explore, the more we realize how small we are in the grand scheme of things, but also how much potential we have to uncover the secrets of the cosmos. The universe is vast, and our journey through it has only just begun. As we venture further into the depths of space, the mysteries only seem to multiply, and with each new discovery, our perception of reality continues to evolve. One of the most profound questions is the nature of time itself. In our everyday experience, time flows in one direction, always forward. But in the far reaches of space, near the edge of black holes, time behaves in bizarre and unexpected ways. Thanks to the theory of general relativity, we know that time can slow down in the presence of a strong gravitational field, a phenomenon known as time dilation. The closer you get to a massive object like a black hole, the slower time passes relative to an observer far away. If you were to hover near the event horizon of a black hole, time for you would appear to move at a crawl compared to the rest of the universe. From your perspective, the universe outside might speed by, with years or even centuries passing in what feels like minutes to you. This strange warping of time leads us to wonder whether time itself is as rigid as we once thought, or if it might bend and fold in ways we've yet to fully understand. Connected to the fabric of time is the idea of space-time, the four-dimensional construct that fuses the three dimensions of space with the dimension of time. It's within this space-time framework that the universe unfolds, with everything from the smallest particles to the largest galaxies moving and interacting within it. But what if space-time isn't the ultimate fabric of the universe? Some theories suggest that there could be even more fundamental layers of reality beneath space-time, dimensions or entities we can't yet perceive directly. String theory, for example, proposes that all particles are actually tiny vibrating strings of energy, each with its own frequency. These strings could be embedded in higher dimensional spaces, with some dimensions compacted so tightly that they're invisible to us. If this theory holds true, the universe may contain as many as 11 dimensions, far beyond the 3 dimensions of space and one of time we experience daily. While the nature of time and space continues to perplex us, we also face the mystery of why the universe exists at all. One of the most puzzling aspects of modern physics is the cosmological constant problem, which refers to the discrepancy between the observed value of dark energy, the mysterious force driving the universe's accelerated expansion, and the predicted value from quantum field theory. The prediction suggests that the energy density of empty space should be astronomically higher than what we observe. This discrepancy, sometimes called the vacuum catastrophe, suggests that there is something fundamentally missing in our understanding of the universe. Some physicists speculate that solving this problem could require a major revision of the laws of physics as we currently know them, possibly pointing to new forms of energy or matter that we haven't yet discovered. Dark energy itself is one of the greatest puzzles in modern cosmology. As mentioned earlier, it is responsible for pushing the universe apart at an ever-accelerating rate. This expansion was discovered in the late 1990s, when astronomers observed distant supernovae and realized they were farther away than they should be if the universe's expansion was slowing down, as once thought. Dark energy, which accounts for about 70% of the universe's total energy content, remains an enigma. We don't know what it is, how it works, or why it exists, but its influence on the universe is undeniable. Some have suggested that dark energy might be related to the quantum fluctuations of empty space, while others propose it could be evidence of a multiverse, with our universe being just one bubble in a larger cosmic foam. Whatever the explanation, understanding dark energy could unlock the key to the universe's ultimate fate. Speaking of the universe's fate, one of the most thought-provoking questions in cosmology is how the universe will end. There are several competing theories, each more dramatic than the last. One possibility is the Big Freeze, where the universe continues to expand until it becomes a cold, dark, and desolate place. In this scenario, stars will eventually burn out, galaxies will drift apart, and the universe will fade into a lifeless void, with only the remnants of black holes and subatomic particles left behind. Another possibility is the Big Crunch, where the expansion of the universe could reverse, causing everything to collapse back in on itself. This would result in a cataclysmic event that might mirror the Big Bang, perhaps even leading to the birth of a new universe. A third, more extreme theory is the Big Rip, in which the expansion of the universe accelerates to the point where it tears apart galaxies, stars, planets, and eventually even atoms themselves, leaving nothing but isolated particles in an empty, ever-expanding void. While these grand cosmological events may be billions of years away, there are still mysteries unfolding right here in our cosmic neighborhood. One of the strangest recent discoveries involves Oumuamua, an interstellar object that passed through our solar system in 2017. Unlike typical comets or asteroids, Oumuamua's elongated, cigar-like shape and its unusual acceleration puzzled scientists. It didn't behave like any object we'd seen before. Some researchers speculated that it could be a piece of debris from another star system, while others even floated the possibility that it might be an artificial object, perhaps a probe sent by an advanced civilization. While there's no solid evidence to support the latter claim, the fact that we now know interstellar objects can pass through our solar system opens up new possibilities for exploration. Future missions could intercept and study these objects, providing insights into the building blocks of other star systems. Beyond mysterious visitors like Oumuamua, the solar system itself holds many surprises. One of the most intriguing is the dwarf planet Pluto, which, despite being demoted from full planet status in 2006, remains a fascinating object of study. The New Horizons mission, which flew by Pluto in 2015, revealed a surprisingly dynamic world with vast ice plains, towering mountains of frozen nitrogen, and even evidence of cryovolcanoes, volcanoes that spew ice instead of molten rock. Pluto's surface is also dotted with strange, polygonal patterns that suggest it might be slowly shrinking as its interior cools. These unexpected findings have reignited interest in the outer reaches of the solar system, leading scientists to question what other surprises might await in the distant Kuiper Belt, a region of icy objects beyond Neptune. Another curiosity lies in the rings of Saturn. While Saturn's rings are easily the most iconic, other gas giants like Jupiter, Uranus, and Neptune also have ring systems. But what makes Saturn's rings so fascinating is their sheer size and brightness, coupled with the mystery of their origin. Some scientists believe the rings could be relatively young, perhaps only a few 100 million years old, and might have formed when a moon or comet was torn apart by Saturn's gravity. Others speculate that the rings are much older, remnants of the early solar system. Either way, the rings are slowly disappearing, as material from them drifts into Saturn's atmosphere. In a few 100 million years, they may be gone entirely, leaving future observers to wonder if they ever existed at all. The moons of the outer planets also hold remarkable potential for discovery. One of the most exciting is Titan, Saturn's largest moon, which has a thick atmosphere and liquid methane lakes on its surface. The presence of stable liquids on Titan makes it one of the few places in the solar system where some form of life might exist. Meanwhile, Europa, a moon of Jupiter, hides a global ocean beneath its icy crust, which could harbor microbial life in a deep, dark ocean heated by tidal forces. Upcoming missions like NASA's Europa Clipper aim to explore these worlds in greater detail, searching for signs of life or at least the conditions that could support it. Even Mars, our closest planetary neighbor, continues to captivate our attention. Though it's a cold, barren desert today, evidence suggests that Mars once had a much thicker atmosphere, flowing water, and possibly even oceans. The discovery of ancient river valleys and lake beds points to a wetter, warmer past, and recent findings of underground water ice have sparked hopes of future human colonization. The search for microbial life on Mars is ongoing, with missions like the Perseverance rover collecting samples that could one day be returned to Earth for analysis. If life ever existed on Mars, even in the form of simple bacteria, it would revolutionize our understanding of life's potential in the universe. With so many mysteries, both near and far, it's clear that space holds endless opportunities for exploration and discovery. The more we learn, the more we realize how much we don't know, and each new revelation pushes the boundaries of human knowledge further into the unknown. From the possibility of life on distant moons to the fate of the universe itself, space continues to inspire wonder, challenge our understanding, and remind us that the cosmos is far stranger and more complex than we could ever have imagined. And as we continue to explore, we may one day find that the answers to the universe's greatest mysteries are even more incredible than we dared to dream. As we continue our journey into the boundless cosmos, we begin to grasp just how much more there is to learn and uncover. One of the greatest mysteries still surrounding the universe is the true nature of black holes and their relationship to the universe's most fundamental forces. Black holes are so dense that not even light can escape their gravitational pull. But what really happens inside them remains a topic of intense scientific debate. At the center of a black hole lies the singularity, a point of infinite density where the known laws of physics break down. Everything we understand about space, time, and matter collapses into a mathematical paradox at the singularity, challenging our very conception of reality. A particularly perplexing aspect of black holes is the information paradox. According to the laws of quantum mechanics, information cannot be destroyed, even if it falls into a black hole. However, classical physics tells us that anything crossing the event horizon of a black hole is lost forever, including the information that describes the object. This contradiction has led to a heated debate among physicists. Some suggest that information might be encoded in the Hawking radiation that slowly leaks from black holes over time, while others propose more radical ideas, like the possibility that black holes could be gateways to other universes, with information reappearing in a completely different part of the cosmos. One of the most intriguing theories to arise from this debate is the holographic principle, which suggests that all the information contained within a volume of space can be described by data encoded on the boundary of that space, much like a hologram. In this view, the entire universe could be thought of as a kind of hologram, where three-dimensional reality emerges from information stored on a two-dimensional surface. This idea, though highly speculative, has gained traction in certain branches of theoretical physics and could lead to new insights into the true nature of space-time and gravity. As we continue to explore black holes, another mind-bending concept has emerged, that they might not only consume matter, but also be capable of creating new universes. Some physicists propose that black holes could act as cosmic seeds, with the intense conditions at the singularity giving birth to entirely new universes on the other side. In this scenario, each black hole in our universe could be the progenitor of another universe, with its own unique laws of physics and constants. This idea is linked to the concept of a multiverse, where our universe is just one of an infinite number of universes, each with its own distinct properties. If true, this theory would drastically expand our understanding of existence and place our universe within an even grander cosmic landscape. While black holes are often associated with destruction, There are also more creative phenomena in the cosmos, such as star formation in vast, colorful regions called nebulae. Nebulae are the birthplaces of stars, where clouds of gas and dust collapse under gravity to form new stellar bodies. Some of the most famous nebulae include the Eagle Nebula, home to the iconic Pillars of Creation, and the Orion Nebula, one of the brightest and most well-studied star-forming regions in the sky. These stellar nurseries are not only breathtakingly beautiful, but also crucial to the life cycle of the universe. The stars formed in nebulae eventually die in spectacular supernova explosions, scattering heavy elements like carbon, oxygen, and iron throughout space, elements that will later become the building blocks for new stars, planets, and even life. Supernovae themselves are some of the most powerful and awe-inspiring events in the universe. When a massive star exhausts its nuclear fuel, it can no longer support its own weight, leading to a catastrophic collapse and explosion. This supernova can outshine an entire galaxy for a short period, releasing more energy in a few seconds than the sun will emit over its entire 10 billion-year lifespan. The shock waves from supernovae can trigger the formation of new stars by compressing nearby clouds of gas and dust, continuing the cosmic cycle of death and rebirth. What's left behind after a supernova is often either a neutron star or a black hole, depending on the mass of the original star. Neutron stars, though less well-known than black holes, are equally fascinating. These incredibly dense objects are formed from the remnants of supernova explosions and are made almost entirely of neutrons. A single teaspoon of neutron star material would weigh about 6 billion tons on Earth. Some neutron stars spin rapidly, emitting beams of radiation that sweep across the sky like a lighthouse. These rapidly spinning neutron stars are known as pulsars. One of the most remarkable pulsars is the Crab pulsar, located in the center of the Crab Nebula, which spins 30 times per second and is a powerful source of radio, optical, X-ray, and gamma-ray radiation. While supernovae and neutron stars demonstrate the violent and energetic processes at work in the universe, there are also more subtle and elusive phenomena, such as dark matter. Unlike normal matter, dark matter doesn't emit, absorb, or reflect light, making it invisible to telescopes. Yet, we know it exists because of its gravitational effects on galaxies and galaxy clusters. Without dark matter, galaxies would not have enough mass to hold themselves together, and they would fly apart as they spin. Scientists estimate that dark matter makes up about 27% of the universe's total mass and energy content, far more than the 5% that is ordinary matter. However, despite decades of research, we still have no direct detection of dark matter, leaving its true nature one of the most profound mysteries in cosmology. Alongside dark matter is its equally mysterious counterpart, dark energy. As mentioned before, dark energy is driving the accelerated expansion of the universe, and it makes up about 68% of the universe's total energy. The discovery of dark energy in the late 1990s was a complete surprise, as most scientists at the time expected the expansion of the universe to be slowing down due to gravity. Instead, they found that the universe is expanding faster than ever, suggesting the presence of an unknown force counteracting gravity on cosmic scales. Understanding dark energy is one of the biggest challenges in modern physics, as it could reveal fundamental truths about the fate of the universe and the nature of reality itself. While the mysteries of dark matter and dark energy continue to baffle scientists, closer to home, we've discovered some truly unusual planets beyond our solar system. One of the strangest is HD 189733b, a hot Jupiter exoplanet located 63 light-years away. This gas giant orbits so close to its parent star that its atmosphere reaches temperatures of over 1,000 degrees Celsius. What makes HD 189733b particularly bizarre, though, is its weather. The planet experiences winds of up to 5,400 miles per hour, about 7 times the speed of sound, and its atmosphere contains silicate particles, meaning that it rains molten glass sideways at extreme speeds. Another unusual exoplanet is Kepler 16b, a planet that orbits not one but 2 stars, much like the fictional planet Tatooine from Star Wars. This makes Kepler 16b part of a class of planets, known as circumbinary planets, where a planet orbits a pair of stars instead of a single one. Such systems were once thought to be too unstable to support planets, but Kepler 16b's existence challenges that assumption and opens up the possibility that life could exist in such exotic environments. Speaking of life, one of the greatest goals of space exploration is to find evidence of life beyond Earth. While Mars is a primary target, with missions like Perseverance searching for signs of past microbial life, there are other exciting possibilities elsewhere in our solar system. For instance, Saturn's moon Enceladus has geysers that spew water vapor into space from a subsurface ocean beneath its icy shell. This ocean, warmed by tidal forces, could harbor the conditions necessary for life. Similarly, Jupiter's moon Europa also has a subsurface ocean, making it another prime candidate for the search for extraterrestrial life. As we expand our search beyond the solar system, the discovery of potentially habitable exoplanets continues to fuel the excitement of finding life elsewhere. One of the most promising candidates is Proxima Centauri b, an Earth-sized planet orbiting in the habitable zone of Proxima Centauri, the closest star to the Sun. While we don't yet know if Proxima b has an atmosphere or liquid water, its location in the habitable zone suggests it could have the right conditions for life. The discovery of an Earth-like planet so close to our solar system raises the tantalizing possibility that life could exist just a few light years away. With so many mysteries still waiting to be unraveled, our exploration of the cosmos is only just beginning. The universe is a vast and intricate tapestry, full of wonders that challenge our understanding and stretch the limits of human imagination. As we continue to explore the stars, galaxies, and even the fundamental forces that shape reality itself, one thing is certain. The more we learn about space, the more we realize how much remains to be discovered. Every answer leads to new questions, and every mystery solved reveals deeper complexities. Our quest to understand the universe will likely continue for generations, and with each new discovery, we come one step closer to unraveling the secrets of the cosmos. As we push the boundaries of our understanding further, we arrive at one of the most intriguing and controversial topics in the study of the universe: the possibility of intelligent extraterrestrial life. The search for extraterrestrial intelligence, SETI, has captivated the minds of scientists and the public alike for decades. Using radio telescopes to scan the skies for signals from advanced civilizations, SETI has yet to find definitive proof of alien life. But the sheer size of the universe makes it seem unlikely that Earth is the only planet to have developed life, let alone intelligent life. Given the billions of stars in the Milky Way alone, many with planetary systems of their own, the statistical probability that life exists elsewhere is high. The real question is, why haven't we found it yet? This brings us to the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for their existence. If intelligent life is common in the universe, why haven't we detected any signals or found any signs of alien technology? Several explanations have been proposed to solve the paradox. One possibility is that intelligent civilizations are simply too far apart in space and time. The vast distances between stars mean that even if a civilization sent out a signal, it could take thousands or millions of years to reach us. Additionally, civilizations may rise and fall over time, with many potentially having existed and gone extinct long before we even developed the technology to search for them. Another explanation for the Fermi paradox is the idea of the Great Filter. This theory suggests that there is a stage in the development of life that is incredibly difficult to surpass, and most civilizations never make it past this point. The filter could be in our past. Perhaps the emergence of intelligent life is exceedingly rare. Or it could be in our future, with technological civilizations doomed to self-destruction before they can achieve interstellar communication or travel. If the Great Filter lies ahead of us, it would imply that humanity faces a critical challenge, whether it be nuclear war, climate catastrophe, or some other existential threat, that we must overcome to survive in the long term. There's also the possibility that intelligent extraterrestrial civilizations are deliberately avoiding us. This idea, known as the zoo hypothesis, suggests that advanced civilizations might be aware of our existence, but choose not to interfere, much like we avoid interacting with wildlife preserves. They may be observing us from afar, waiting for humanity to reach a certain level of technological or societal maturity before making contact. Alternatively, they might simply have no interest in communicating with a species as primitive as ours by their standards, much like how we don't attempt to communicate with ants. One of the more speculative solutions to the Fermi paradox is the idea that we may be living in a simulation. According to this theory, advanced civilizations could have developed the ability to create highly sophisticated simulations of entire universes, and we might be living inside one of these simulations without even realizing it. If this is the case, the reason we haven't encountered any extraterrestrial civilizations could be that they don't exist in our simulated universe, or the creators of the simulation simply haven't programmed them into our reality. While this theory is impossible to prove or disprove, it raises profound questions about the nature of reality itself. Leaving aside the speculative, let's turn to the tangible advancements in our search for life beyond Earth. One of the most exciting developments in recent years is the discovery of potentially habitable exoplanets. Thousands of these planets have been identified, with many residing in the so-called habitable zone of their star, where conditions might be just right for liquid water to exist, a key ingredient for life as we know it. The discovery of the TRAPPIST-1 system, with its 7 Earth-sized planets, 3 of which lie in the habitable zone, has generated considerable excitement. These planets are located just 40 light-years away, making them prime candidates for further study in the search for signs of life. Future space missions are set to greatly enhance our ability to study these distant worlds. The James Webb Space Telescope, JWST, launched in 2021, is already providing unprecedented insights into the atmospheres of exoplanets. By analyzing the light passing through a planet's atmosphere as it transits its star, scientists can detect the presence of gases like oxygen, methane, and carbon dioxide, potential indicators of biological activity. If we were to detect a combination of these gases in the atmosphere of an exoplanet, it could be a strong sign that life exists there. Additionally, upcoming missions like the European Space Agency's Plato mission and NASA's future space telescopes will continue to expand our understanding of exoplanetary systems. Even within our own solar system, the search for life is far from over. One of the most intriguing prospects is Saturn's moon Enceladus, which, as previously mentioned, has geysers ejecting water vapor into space from a subsurface ocean. Recent studies have found organic molecules in the plumes, raising the tantalizing possibility that microbial life might exist in the hidden ocean beneath Enceladus' icy crust. Similarly, Jupiter's moon Europa, with its own subsurface ocean, remains one of the most promising places to search for extraterrestrial life. Missions like NASA's Europa Clipper, scheduled to launch in the near future, will attempt to explore these moons more thoroughly, looking for signs of life in their dark, hidden oceans. Of course, the search for life beyond Earth extends beyond the possibility of finding intelligent civilizations or microbial life. Astrobiologists are also interested in discovering extremophiles, organisms that can survive in extreme environments. On Earth, extremophiles thrive in some of the most inhospitable places, from the boiling hot springs of Yellowstone to the freezing waters beneath Antarctica's ice sheets. These hardy organisms suggest that life might be able to survive in environments previously thought to be too extreme, such as the frigid surface of Mars or the high-radiation environment of Europa. By studying extremophiles, scientists are expanding the range of conditions in which life could potentially exist elsewhere in the universe. While the search for life is one of the most compelling aspects of space exploration, there are other technological developments that could dramatically change our future in space. One such development is the concept of space mining. Asteroids are rich in valuable minerals and metals, including iron, nickel, and even platinum, which could be harvested for use in space exploration and on Earth. Some estimates suggest that a single asteroid could contain more platinum than has ever been mined in human history. Companies like Planetary Resources and Deep Space Industries are already working on the technology to mine asteroids, and space agencies like NASA are exploring how to extract resources from the Moon and Mars to support future missions. The ability to harvest resources from space could be a game-changer for human colonization of other planets. Rather than launching all the necessary materials from Earth, Future astronauts could use resources from the moon or asteroids to build habitats, manufacture fuel, and support life. This would significantly reduce the cost and complexity of deep space missions, potentially enabling long-term human settlements on the moon, Mars, or even further out into the solar system. In addition, the ability to extract water from lunar ice or Martian soil could provide a sustainable source of drinking water and oxygen for astronauts, making permanent colonies more feasible. As we consider the future of human space exploration, it's clear that one of the most ambitious goals is the colonization of Mars. Elon Musk's SpaceX has set its sights on sending humans to Mars within the next decade, with the ultimate goal of establishing a self-sustaining colony. While the challenges are immense, from the harsh Martian climate to the psychological effects of long-term isolation, the potential rewards are equally great. A successful Mars colony could serve as a backup for humanity, ensuring the survival of our species in the event of a catastrophe on Earth. It could also pave the way for further exploration of the outer solar system, possibly leading to colonies on moons like Europa or Titan in the distant future. Colonizing Mars would require not only technological innovation, but also a new way of thinking about how humans interact with space. Long-duration space travel poses unique challenges, including the effects of microgravity on the human body, radiation exposure, and the psychological stress of isolation. Solutions to these challenges could include artificial gravity habitats, enhanced radiation shielding, and advanced life support systems that recycle air and water with near-perfect efficiency. Space farming, where crops are grown in controlled environments, would be crucial for providing a sustainable food supply on Mars or other planets. Scientists are already experimenting with growing food in space aboard the International Space Station, with promising results that could one day feed future Martian colonists. Ultimately, the colonization of Mars and beyond will depend on our ability to solve these challenges, but the drive to explore the unknown is as old as humanity itself. From the earliest days of seafaring explorers venturing into uncharted waters to the space race of the 20th century, humans have always been drawn to push the boundaries of the known world. Today, space represents the next frontier, and as we develop the technology to venture further into the cosmos, we will undoubtedly face new challenges and discover new wonders. In the end, the exploration of space is about more than just scientific discovery. It's about the future of humanity. Whether we find life on other planets, colonize Mars, or unravel the mysteries of black holes and dark energy, our quest to understand the universe will continue to inspire and challenge us. The universe is vast, and the more we learn about it, the more we realize how much more there is to discover. As we stand on the edge of this new era of exploration, the possibilities seem endless, and the journey has only just begun. As we push the limits of our understanding even further, the next step in our exploration of the cosmos is to harness the unimaginable power of advanced technologies. These technologies have the potential to transform our ability to explore deep space and could even reshape the future of human civilization. One of the most ambitious concepts in space exploration is the development of fusion propulsion systems. Unlike traditional chemical rockets, which burn fuel and produce thrust, fusion-powered spacecraft would use the same process that powers the sun, nuclear fusion, to generate immense amounts of energy. This would allow spacecraft to travel much faster and farther than ever before, potentially reaching distant planets or even other star systems in a fraction of the time it currently takes. Fusion propulsion is still in its early stages of development, but it represents a major leap forward in our ability to explore the solar system and beyond. A fusion-powered spacecraft could dramatically shorten the journey to Mars, cutting it down from several months to just a few weeks. It could also enable missions to the outer planets, such as Jupiter and Saturn, that would otherwise take decades using conventional propulsion methods. In the long term, fusion propulsion could make interstellar travel a reality, opening the door to missions to nearby star systems like Alpha Centauri. In addition to faster propulsion systems, another transformative technology being developed is the space elevator. The concept of a space elevator involves a massive cable stretching from Earth's surface to a point in geostationary orbit, about 35,000 kilometers above the planet. This cable would allow vehicles to travel up and down between Earth and space, effectively creating a highway to orbit. Such a system could revolutionize space travel by dramatically reducing the cost of sending people and cargo into space, as it would eliminate the need for expensive rockets. While the idea of a space elevator has been around for decades, advancements in materials science, particularly the development of incredibly strong and lightweight materials like carbon nanotubes, are bringing this concept closer to reality. The construction of a space elevator would represent one of the greatest engineering feats in human history, but it could have far-reaching benefits for space exploration and development. With a space elevator in place, we could more easily transport large amounts of supplies to orbiting space stations, build massive structures in space, and even launch missions to other planets with greater efficiency. It would also provide a platform for building and maintaining large-scale space habitats, allowing for long-term human presence in space. Space habitats themselves represent another bold vision for the future of humanity in space. These massive structures, sometimes referred to as O'Neill cylinders or Bernal spheres, are designed to house thousands or even millions of people in self-sustaining environments far from Earth. Inside these habitats, artificial gravity could be generated by spinning the structure, while advanced life support systems would recycle air, water, and waste to create a closed-loop ecosystem. Solar panels or fusion reactors would provide energy, and crops could be grown in vast agricultural sections to provide food. Space habitats could serve as homes for future space explorers, offering an alternative to living on planetary surfaces like Mars, where conditions may be less hospitable. One of the key challenges of establishing a long-term human presence in space, whether on other planets or in space habitats, is developing the technology to support life in extreme environments. Radiation exposure is one of the biggest threats to astronauts, especially on long-duration missions beyond Earth's protective magnetic field. Without proper shielding, radiation from the sun and cosmic rays could cause serious health problems, including cancer. To combat this, scientists are exploring a variety of solutions, such as building habitats underground or using advanced materials that can block radiation. Some have even suggested using water as a shield, as it is highly effective at absorbing radiation. Another challenge is providing a sustainable source of food for astronauts on long missions. Growing food in space presents unique difficulties, such as limited space, low gravity, and the need for careful resource management. However, advances in space farming technology are making it possible to grow crops in microgravity environments. Researchers aboard the International Space Station have successfully grown lettuce, radishes, and other crops, and experiments with hydroponics and aeroponics, growing plants without soil, are showing promise. These techniques could one day be used to grow food in space habitats or on the surface of Mars, providing a reliable food source for future space explorers. As our technological capabilities grow, so too does the potential for mining resources in space. One of the most promising targets for space mining is the Moon. The lunar surface contains valuable resources, including water ice, which can be used to produce oxygen for breathing and hydrogen for rocket fuel. Extracting and processing these resources on the Moon could greatly reduce the cost of space exploration, as it would eliminate the need to launch materials from Earth. Additionally, the Moon is rich in helium-3, a rare isotope that could be used as fuel for nuclear fusion reactors. If we can develop the technology to mine and transport these resources, the Moon could become a critical outpost for future missions to Mars and beyond. Asteroid mining is another exciting possibility. Many asteroids are composed of materials like iron, nickel, and precious metals, which could be used for construction or brought back to Earth for industrial purposes. Some asteroids also contain water, which could be used to produce rocket fuel in space. Mining these resources could provide the raw materials needed to build large space structures, such as habitats or spacecraft, without having to launch them from Earth. This would greatly reduce the cost of space exploration and open up new possibilities for human expansion into the solar system. As we look further into the future, one of the most exciting possibilities is the development of warp drives or other forms of faster-than-light travel. While these concepts remain purely theoretical at the moment, they have captured the imagination of scientists and science fiction writers alike. The idea of a warp drive, first popularized by the Star Trek series, involves bending or warping space-time to allow a spacecraft to travel faster than the speed of light without violating the laws of physics. Recent research by physicists, such as Miguel Alcubierre, has shown that warp drives might be possible in theory, though the energy requirements would be enormous, far beyond anything we can currently produce. Another theoretical approach to faster-than-light travel is the use of wormholes. Wormholes are shortcuts through space-time that could, in principle, allow for instantaneous travel between two distant points in the universe. While no evidence of wormholes has been found, and their stability remains questionable, they represent an intriguing possibility for future space travel. If we could harness the power of wormholes, it would revolutionize our ability to explore the galaxy, making interstellar travel as routine as crossing a continent. In parallel with these advanced propulsion technologies, artificial intelligence, AI, will likely play a key role in the future of space exploration. AI is already being used to assist in mission planning, data analysis, and autonomous spacecraft navigation, but its potential goes far beyond that. In the future, AI could be used to manage entire space missions, from piloting spacecraft to making real-time decisions during emergencies. Robots equipped with AI could also be used to explore distant planets and moons, carrying out tasks too dangerous or difficult for humans. For example, AI-powered rovers could be sent to explore the surface of Europa or Enceladus, searching for signs of life in their icy oceans. AI could also play a crucial role in building and maintaining space habitats. Robots could construct habitats on the Moon or Mars using materials found on-site, reducing the need to transport building materials from Earth. Once the habitats are operational, AI systems could monitor and manage life support systems, ensuring that air, water, and food are produced and recycled efficiently. This would allow humans to focus on scientific research and exploration, while AI handles the day-to-day operations of the habitat. The combination of AI and advanced robotics could also enable humanity to establish a permanent presence on other planets. On Mars, for example, robots could be sent ahead of human explorers to build shelters, extract resources, and prepare the surface for human habitation. These robots could operate autonomously or be remotely controlled by humans on Earth or in orbit. By the time astronauts arrive, much of the infrastructure needed for a colony could already be in place, reducing the risks and costs associated with human exploration. As we look even further into the future, we may one day be able to modify our own biology to adapt to the harsh conditions of space. Genetic engineering and biotechnology could allow humans to survive in environments that are currently inhospitable, such as the low-gravity environments of Mars or the radiation-filled depths of space. Scientists are already experimenting with genetic modifications that could make humans more resistant to radiation or help them cope with long periods of isolation. While these technologies are still in their infancy, they could eventually enable humans to thrive in environments that would otherwise be impossible to colonize. The future of space exploration is not just about technology, however. It's also about how we, as a species, choose to explore and settle the cosmos. As we venture into space, we will face ethical and philosophical questions about how to manage and share the resources of space. Will space become the domain of a few wealthy nations and corporations, or will it be accessible to all of humanity? How will we ensure that space is explored and developed in a way that respects the rights of future generations and preserves the cosmic environment? These are questions that we must begin to address now, as the era of space colonization approaches. In the end, space exploration is not just a scientific endeavor, it's a human one. It's about our desire to understand the universe and our place in it. It's about the curiosity and ingenuity that have driven us to explore the unknown for millennia. As we continue to push the boundaries of what's possible, we may one day find that space is not just a frontier to explore, but a new home for humanity. Whether we establish colonies on Mars, travel to distant star systems, or discover new forms of life, our journey into the cosmos will shape the future of our species in ways we can only begin to imagine. The universe is vast, and we are just beginning to take our first steps into it. The possibilities are limitless, and the adventure has only just begun. As we stand on the precipice of this new era in space exploration, the possibilities seem more expansive than ever, and with each technological advancement, the dream of becoming a spacefaring civilization moves closer to reality. One of the most profound and forward-thinking concepts being discussed is the potential for human beings to move beyond physical exploration and into the realm of digital immortality. This idea is rooted in the concept of mind uploading, where human consciousness could be transferred into a digital format, allowing us to explore space without the limitations of our biological bodies. Mind uploading, though speculative at this point, is based on the idea that our consciousness, the sum of our thoughts, memories, and personality, could be mapped and digitized. If this were possible, digital versions of ourselves could theoretically be uploaded into advanced robotic bodies or even spacecraft, making us immune to the physical dangers of space travel, such as radiation, lack of oxygen, and the immense distances between stars. In this scenario, humans could explore the farthest reaches of the universe without concern for the frailties of the human body. This concept raises deep philosophical and ethical questions about the nature of identity and what it means to be human. Would a digital copy of ourselves truly be us? And what happens to our biological form once our consciousness is uploaded? This idea of transcending biological limitations to explore space is not just limited to mind uploading. Genetic engineering and bioenhancement technologies could be used to adapt the human body to the extreme environments of space. Future astronauts might have enhanced radiation resistance, improved lung capacity to deal with thin atmospheres, or even the ability to hibernate for extended periods, similar to the way some animals can slow their metabolism to survive harsh conditions. Hibernation, or cryosleep, has long been a staple of science fiction, but researchers are beginning to explore ways to induce a similar state in humans for long-duration space missions. By slowing the body's metabolic processes, we could reduce the resources needed for long space journeys, allowing humans to travel to distant planets or even other star systems more feasibly. In the same vein, advances in artificial intelligence, AI, and robotics are set to play a pivotal role in the future of space exploration. AI is already revolutionizing many aspects of space science, from navigating spacecraft to analyzing vast amounts of data collected by telescopes and space probes. In the near future, AI systems could become even more autonomous, making real-time decisions during missions to distant planets and moons without needing to wait for instructions from Earth. This is especially crucial for missions to deep space destinations where communication delays can span minutes or even hours. AI-powered robots could also perform tasks that would be too dangerous or physically demanding for humans. For example, robotic explorers equipped with AI could be deployed to the surface of Venus, where temperatures and atmospheric pressure are so extreme that any human mission would be unfeasible with current technology. These robots could analyze the planet's geology, search for signs of past water activity, or even conduct experiments that help us understand how Venus became the scorched world it is today. AI is also set to revolutionize how we interact with space habitats and manage colonies on other planets. Advanced AI systems could monitor life support systems, manage resources, and even assist with the construction of new habitats on the Moon, Mars, or beyond. By automating these processes, we could ensure that human settlers have everything they need to survive and thrive in space, reducing the risk of human error and allowing astronauts to focus on exploration and research. While AI and robotics are essential to the future of space exploration, another area of innovation lies in space manufacturing. In recent years, 3D printing technology has made significant strides, and it's now being adapted for use in space. NASA and private companies are developing 3D printers that can manufacture tools, parts, and even entire structures in space using materials found on the Moon, Mars, or asteroids. This technology could be a game changer, as it would allow future missions to print the tools and equipment they need on-site, rather than carrying everything from Earth. Imagine a Mars mission where astronauts use 3D printers to create habitats from Martian soil, or a lunar colony that builds solar panels directly on the Moon's surface using locally sourced materials. This ability to manufacture in space would not only make space exploration more sustainable, but could also significantly reduce the cost and logistical challenges of sending humans to other planets. In fact, sustainable living in space is one of the most critical challenges we face as we look toward long-term human settlement on other planets. Life support systems that can recycle air, water, and waste are essential for any mission beyond Earth. But in the future, we may develop entirely self-sustaining space habitats. These habitats would be closed-loop ecosystems, where waste is recycled into usable resources, and energy is generated from renewable sources like solar power. By creating environments that can support human life indefinitely, we would be able to establish permanent colonies on the Moon, Mars, and other celestial bodies. One of the most ambitious visions for space colonization involves the concept of terraforming. Terraforming refers to the process of transforming the environment of a planet to make it more Earth-like, potentially allowing humans to live there without the need for life support systems. Mars is often cited as the most likely candidate for terraforming, as it has polar ice caps that could be melted to create oceans, and its atmosphere, while thin, contains carbon dioxide that could be converted into oxygen through advanced technology. While the concept of terraforming is still far beyond our current capabilities, scientists are already thinking about the steps we would need to take to make it a reality. This might involve releasing greenhouse gases into the Martian atmosphere to warm the planet, melting the polar ice caps to create bodies of water, or introducing genetically engineered plants and microbes that could survive in Mars' harsh environment and begin producing oxygen. While these ideas are speculative, they represent the ultimate goal of making other planets habitable for humans, turning them into new homes for our species. However, even if we don't terraform entire planets, we might create space colonies that exist independently of any planetary surface. These so-called space cities could be massive structures orbiting the Earth, Moon, or even other planets. Space cities would be completely self-contained environments, with artificial gravity, breathable air, and everything needed to support human life. Some scientists envision these cities being built in the asteroid belt, where they could be close to valuable resources for mining and industry. These space colonies would be the next step in humanity's expansion into the cosmos, representing a new way of living that goes beyond the limitations of our home planet. As we consider the future of human life in space, we also face profound philosophical and ethical questions. What will it mean to be human in a world where we can alter our biology, upload our consciousness, or live in entirely artificial environments? How will we ensure that the resources of space are shared fairly among all nations and peoples? And how will we protect the pristine environments of other planets and moons from contamination by human activity? The ethical considerations of space exploration are already being discussed by scientists, policymakers, and ethicists. For example, planetary protection is a growing concern as we send more missions to potentially habitable worlds like Mars and Europa. We must take great care to avoid contaminating these environments with Earth microbes, which could not only compromise our search for extraterrestrial life, but also disrupt any ecosystems that might exist there. Similarly, as we begin to mine asteroids or extract resources from the Moon, we must think carefully about the environmental impact of these activities and how to manage them sustainably. Another ethical consideration is how we approach contact with potential extraterrestrial civilizations. If we were to discover intelligent life beyond Earth, it would be the most profound event in human history, but it also raises difficult questions. How should we communicate with extraterrestrial beings, and what rights would they have? Should we attempt to make contact, or would it be wiser to observe from a distance to avoid any unintended consequences? These questions, though speculative, will become increasingly relevant as our ability to explore and interact with the universe grows. Looking further ahead, some scientists believe that humanity's future lies not just in space exploration, but in becoming a multiplanetary species. In the distant future, we may not only colonize the Moon, Mars, and the moons of the outer planets, but we might also send human explorers to distant star systems. Projects like Breakthrough Starshot, which aims to send tiny, light-powered spacecraft to Alpha Centauri, are already laying the groundwork for interstellar travel. While sending humans to other star systems remains a distant dream, the pace of technological advancement suggests that it may be within reach in the coming centuries. As we expand into space, we will need to redefine what it means to be human and how we relate to the universe. Space will not only be a place for exploration and scientific discovery, but also a new frontier for art, culture, and society. The space habitats of the future may house not only scientists and engineers, but also artists, philosophers, and people from all walks of life, each bringing their unique perspectives to the challenges and opportunities of life beyond Earth. The possibilities are as vast as the universe itself. From mining asteroids to building space cities, from exploring distant star systems to potentially finding other forms of life. The future of space exploration is a journey of discovery that promises to reshape our understanding of the cosmos and our place within it. While the challenges are immense, the potential rewards are even greater. As we continue to push the boundaries of human knowledge and capability, we are embarking on the greatest adventure of all, our journey into the stars. The future of space exploration is not just about science and technology, but about the very essence of human curiosity, creativity, and the desire to reach for the unknown. The universe beckons, and we are just beginning to answer its call. As we venture further into the unknown realms of space, it becomes clear that the ultimate frontier is not just the physical universe, but the fundamental fabric of reality itself. As our understanding of the cosmos deepens, new questions arise about the very nature of existence, questions that challenge the boundaries of science, philosophy, and even consciousness. These emerging mysteries promise to guide us on a path not only of exploration, but of profound transformation in how we perceive the universe and our role within it. One of the most profound ideas that has gained traction in recent years is the concept of the multiverse. According to this theory, our universe is just one of an infinite number of universes, each with its own unique set of physical laws, constants, and dimensions. The idea of the multiverse arises naturally from certain interpretations of quantum mechanics, string theory, and cosmic inflation. If the multiverse exists, it means that our universe may be just a small bubble in a much larger cosmic sea, with countless other universes forming and collapsing around us. Each of these universes could be radically different from our own, with alternate versions of physics, matter, and perhaps even life. The implications of the multiverse theory are staggering. For one, it would mean that the fine-tuning of the physical constants that allow life to exist in our universe, such as the strength of gravity and the charge of the electron, might not be as improbable as we once thought. In a multiverse, there could be universes where these constants take on different values, resulting in realities where stars don't form, planets don't coalesce, or life as we know it is impossible. Our universe, then, could simply be one where the conditions happen to be just right for life to arise, rather than the result of some grand cosmic design. However, the multiverse raises deep philosophical questions as well. If there are infinite universes, does that mean there are infinite versions of you? Are there alternate realities where you made different choices, or where entirely different events unfolded throughout history? The multiverse could suggest that every possible outcome of every event happened somewhere, in some universe, leading to a reality where every possibility is realized. This challenges our very understanding of free will, identity, and the uniqueness of our own existence. While the multiverse remains a speculative concept, recent advancements in quantum physics are pushing the boundaries of what we know about reality. Quantum mechanics itself, with its strange and counterintuitive rules, has shown us that the universe operates in ways that often defy classical logic. For example, the famous double-slit experiment reveals that particles like electrons can behave both as particles and waves, depending on how they are observed. This phenomenon, known as wave-particle duality, suggests that reality at the quantum level is deeply intertwined with observation and measurement, raising profound questions about the nature of consciousness and its role in shaping the universe. Some physicists have even speculated that consciousness could be fundamental to the fabric of reality itself. This idea, known as quantum consciousness, posits that the act of observation may play a key role in collapsing the quantum wave function, turning a superposition of possible outcomes into a single, observable reality. While this remains a controversial hypothesis, it hints at a deeper connection between the mind and the universe, one that could revolutionize our understanding of both physics and consciousness. As we probe deeper into the quantum realm, another emerging area of study is quantum computing. Quantum computers, unlike classical computers, use the principles of superposition and entanglement to process information in ways that are exponentially more powerful than traditional systems. In theory, a fully functional quantum computer could solve problems that are currently intractable for even the most advanced classical supercomputers. This could revolutionize fields as diverse as cryptography, materials science, drug discovery, and artificial intelligence. In the realm of space exploration, quantum computing could play a key role in unlocking new frontiers. One of the most promising applications of quantum computing is in solving complex problems related to space travel, such as optimizing spacecraft trajectories, simulating the behavior of exotic materials for space habitats, or even modeling the quantum effects of gravity near black holes. Quantum computers could also help us better understand the quantum nature of the universe itself, potentially leading to breakthroughs in our understanding of dark matter, dark energy, and the origins of the cosmos. Beyond quantum computing, another exciting area of exploration is the search for a unified theory of everything. A single, all-encompassing theory that would reconcile the seemingly incompatible frameworks of general relativity and quantum mechanics. General relativity describes the behavior of gravity and large-scale structures like stars and galaxies, while quantum mechanics governs the subatomic realm. However, when we try to combine these two theories, such as in the extreme environments of black holes or the Big Bang, they break down, leading to contradictions and infinite results. One of the leading candidates for a theory of everything is string theory. According to string theory, the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings of energy. These strings vibrate at different frequencies, giving rise to the various particles and forces we observe. String theory also suggests the existence of additional dimensions beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions could be curled up so tightly that we don't perceive them in our everyday experience. While string theory has yet to be experimentally confirmed, it offers a tantalizing glimpse into the possible underlying structure of the universe. If string theory, or a related framework like M-theory, proves correct, it could provide the long-sought-after bridge between quantum mechanics and general relativity, offering a deeper understanding of the cosmos and potentially unlocking new ways to manipulate the fabric of space-time itself. As we contemplate the vastness of the universe and the strange and beautiful forces that govern it, we must also consider the ethical implications of our exploration. Space exploration, like all human endeavors, carries with it responsibilities, not just to ourselves, but to the universe we are beginning to explore. As we develop the technology to colonize other planets, mine asteroids, and send probes to distant stars, we must think carefully about the long-term consequences of our actions. One of the most pressing concerns is the environmental impact of space exploration. The problem of space debris, or space junk, is already a growing issue in Earth's orbit. Thousands of defunct satellites, rocket stages, and fragments of spacecraft now clutter low Earth orbit, posing a risk to operational satellites and even to astronauts aboard the International Space Station. As we expand our presence in space, we must find ways to manage this debris and prevent it from becoming a hazard to future missions. Beyond Earth's orbit, there is the question of how we will interact with other celestial bodies. Should we treat the Moon, Mars, and other planets as resources to be exploited, or should we preserve them as pristine environments for scientific study? If we discover life on another planet, how will we ensure that we do not inadvertently harm it? These are complex questions that require careful consideration as we move forward in our exploration of the cosmos. In addition to environmental concerns, we must also think about the social and political implications of space exploration. Who will own the resources of space? Will space be governed by international cooperation, or will it become a new frontier for competition and conflict among nations? How will we ensure that the benefits of space exploration are shared equitably, rather than concentrated in the hands of a few powerful actors? These are not just theoretical questions. They are issues that we must begin to address as space exploration becomes an increasingly significant part of the global economy and geopolitical landscape. Despite these challenges, the future of space exploration remains one of the most exciting and hopeful prospects for humanity. As we look to the stars, we are reminded of our shared curiosity, our drive to explore the unknown, and our capacity for innovation and cooperation. The universe is vast, and there is so much left to discover, from the origins of life to the fate of the cosmos itself. In the coming decades, we may witness humans walking on Mars, robots exploring the oceans of Europa, and telescopes peering into the farthest reaches of the observable universe. We may find answers to some of the greatest mysteries of science, or we may encounter new questions that challenge our understanding even further. But whatever the future holds, one thing is certain: our journey into the cosmos is just beginning. The universe is calling us, and as we continue to explore its wonders, we are not only expanding our knowledge, but also expanding our horizons, both as individuals and as a species. Space is the ultimate frontier, and as we venture deeper into its vast expanse, we are embarking on a journey that will define the future of humanity for generations to come. As we continue to chart the unknown, the possibilities seem more limitless than ever before. The universe, with all its mysteries, challenges, and vastness, beckons us forward, pulling humanity into an era where space becomes not just a domain of exploration, but perhaps our very future. The technological, scientific, and philosophical advancements we are on the cusp of achieving will redefine what it means to be human and our role within this grand cosmic tapestry. Each new discovery opens a window to deeper questions, and the more we uncover, the more profound our journey into the universe becomes. One of the key avenues that will shape the future of space exploration and settlement is the idea of interplanetary societies. As we look toward becoming a multiplanetary species, the formation of civilizations on other worlds will become a reality. Mars is the most immediate and likely candidate for human colonization, with several nations and private companies, such as SpaceX, already planning missions to send humans to the Red Planet in the coming decades. But the establishment of Martian colonies is only the beginning. The next question is, what would a society on Mars look like? Life on Mars would be fundamentally different from life on Earth. The Martian atmosphere is thin, composed mostly of carbon dioxide, and the planet experiences extreme temperature fluctuations. Any human settlement would have to be built in controlled, enclosed habitats, perhaps underground or in domed cities that protect inhabitants from the harsh surface conditions, including radiation. These habitats would be self-sustaining, with advanced life support systems recycling air and water, and agricultural systems growing food in artificial environments. These colonies might initially rely on Earth for supplies, but the ultimate goal would be self-sufficiency, creating an economy, infrastructure, and ecosystem entirely independent from Earth. This raises the question of governance. Who will control Mars? Will it be governed by the nations of Earth, by the corporations that finance its colonization, or by the colonists themselves? International agreements like the Outer Space Treaty, which currently governs space activities, state that no nation can claim sovereignty over a celestial body, but the realities of long-term colonization may challenge these frameworks. As new space settlements grow, they may develop their own political systems, economic models, and cultural identities, potentially evolving into entirely new civilizations separate from those on Earth. The development of interplanetary societies also forces us to reconsider our relationship with Earth. As humans expand into space, Earth may come to be viewed not just as our birthplace, but as one planet among many. This could have profound implications for how we manage Earth's resources, protect its environment, and view our responsibilities toward future generations. On the other hand, humanity's expansion into space might also deepen our appreciation for the unique beauty and fragility of our home planet. After all, there may be no place like Earth, even in a universe filled with other worlds. In addition to Mars, there are other destinations within our solar system that could become potential homes for humanity. The moons of Jupiter and Saturn, such as Europa, Ganymede, and Titan, are particularly intriguing. Europa, with its subsurface ocean, could harbor life beneath its icy crust, making it a prime target for future exploration. Colonizing such moons would present significant challenges due to the extreme cold and radiation from their parent planets. But advances in technology could make it possible to establish bases there, perhaps using ice and other local materials to construct habitats. Titan, Saturn's largest moon, is one of the most Earth-like worlds in the solar system in terms of its potential for human settlement. It has a thick atmosphere composed mostly of nitrogen and a surface covered in lakes and rivers of liquid methane and ethane. While these conditions are far from hospitable by Earth standards, Titan's atmosphere offers protection from radiation, and its abundant hydrocarbons could provide valuable resources for fuel and industrial processes. A colony on Titan would look vastly different from anything we have on Earth. But with the right technology, it could become a thriving outpost in the outer solar system. Beyond the solar system, the idea of interstellar travel, the ability to reach other star systems, continues to capture the imagination. The nearest star system to Earth, Alpha Centauri, is about 4.37 light-years away. While this may seem relatively close on a cosmic scale, current propulsion technology would take tens of thousands of years to reach it. However, the development of advanced propulsion systems, such as those based on fusion, antimatter, or even theoretical concepts like the warp drive, could reduce travel time dramatically. One of the most ambitious interstellar projects is Breakthrough Starshot, which aims to send tiny, lightweight spacecraft to Alpha Centauri within a generation. These spacecraft would be powered by laser beams from Earth, accelerating them to a significant fraction of the speed of light. If successful, they could reach the Alpha Centauri system in about 20 years, offering humanity its first real glimpse of another star system. While Breakthrough Starshot focuses on sending robotic probes, the dream of sending human explorers to other stars remains alive, though it will likely require technologies that are still far in the future. Interstellar travel is not just about reaching other star systems for exploration. It is also about securing the long-term survival of humanity. By spreading out across the stars, we could protect ourselves from existential threats that could wipe out civilization on Earth, such as asteroid impacts, supervolcanic eruptions, or even technological disasters like nuclear war. This concept, sometimes referred to as the backup plan for humanity, suggests that if we are to survive as a species in the long run, we must not keep all our eggs in one planetary basket. As we look even further into the future, there is the tantalizing possibility of discovering intelligent extraterrestrial civilizations. The search for extraterrestrial intelligence, SETI, continues to scan the skies for signals from other civilizations, but so far, the search has come up empty. This lack of evidence, despite the high probability of life elsewhere in the universe, is known as the Fermi paradox. Why, if the universe is so vast and likely filled with life, have we not yet encountered any signs of intelligent beings? There are many possible explanations for the Fermi paradox. One is that intelligent civilizations are simply very rare, and we happen to be in a lonely part of the galaxy. Another possibility is that civilizations tend to destroy themselves before they can spread beyond their home planet, succumbing to technological or environmental disasters. Some scientists suggest that advanced civilizations may be deliberately avoiding contact with us, either out of fear, disinterest, or adherence to some form of cosmic non-interference policy, much like the zoo hypothesis, which imagines that advanced extraterrestrials might be observing us from a distance without revealing themselves. It is also possible that we are not looking for the right kind of signals. Advanced civilizations might communicate in ways that are entirely alien to us, using technologies or dimensions of reality that we do not yet understand. They might also exist in forms that are so different from our own that we would not recognize them as intelligent life. For example, they could exist as machine intelligences, having evolved beyond biological bodies, or as energy-based life forms that do not rely on matter at all. If we ever do make contact with an extraterrestrial civilization, it could challenge our fundamental assumptions about life, intelligence, and the universe itself. Despite these unknowns, the search for extraterrestrial life remains one of the most exciting frontiers in science. Whether we find simple microbial life on Mars, complex organisms in the oceans of Europa, or signals from an advanced civilization light years away, such discoveries would forever alter our understanding of life in the universe. They would also force us to confront profound questions about our own place in the cosmos. Are we alone? Or are we part of a vast, interconnected web of life that stretches across the galaxy and beyond? As we contemplate the future of space exploration, we must also recognize that space is not just a physical frontier. It is a cultural and philosophical one as well. Space exploration will inevitably reshape human culture, art, and philosophy in ways that we cannot yet imagine. As we settle new worlds and encounter new challenges, we will develop new ways of thinking, new ways of living, and new ways of understanding the universe. Space may become a crucible for human creativity, spurring innovations not only in science and technology, but also in how we perceive ourselves and our relationship to the cosmos. Art, literature, and music will all be transformed by our experiences in space. The first human settlers on Mars will bring with them the cultural heritage of Earth, but they will also create new cultural forms that reflect their experiences of living on another planet. The Martian sky, with its pale pink sunsets and its two moons, Phobos and Deimos, will inspire new works of art and literature. The isolation of life in space will lead to new forms of storytelling, music, and expression, as people grapple with the challenges of living far from Earth and exploring the unknown. Space exploration will also push the boundaries of human consciousness. As we encounter new worlds, new life forms, and perhaps new civilizations, we will be forced to confront the limits of our own understanding. We will have to ask ourselves what it means to be human in a universe that is far stranger and more complex than we ever imagined. This journey into the unknown is not just a physical one. It is a journey of the mind, a quest for knowledge, meaning, and connection in a universe that is both beautiful and incomprehensibly vast. In the end, the future of space exploration is not just about reaching new destinations. It is about expanding the horizons of human possibility. As we push further into the cosmos, we are not just exploring new worlds. We are exploring new ways of being, thinking, and creating. The universe is infinite in its mysteries, and as we unlock its secrets, we will discover new dimensions of ourselves. The future of space is the future of humanity, and it promises to be an adventure unlike any we have ever known. As we continue to dream about our place among the stars, we're on the brink of realizing the most audacious ambitions humanity has ever set for itself. In the near future, space will no longer just be a distant frontier observed through telescopes or visited briefly by astronauts. It will become a domain where humans live, work, create, and evolve in ways we are only beginning to imagine. The transition from temporary expeditions to permanent settlements will mark a profound shift, one that will challenge every facet of our understanding, scientific, cultural, and even spiritual. With this next chapter, we begin to envision a future where space is not just a destination, but a new home. The development of space habitats, artificially created environments where humans can live sustainably for long periods, will be a cornerstone of this new era. Today, concepts for these habitats range from orbital stations to lunar bases and vast colonies in deep space. While the International Space Station, ISS, has served as a vital proving ground for life in microgravity, the next generation of space habitats will need to be much larger, more self-sufficient, and capable of supporting not just astronauts on short missions, but entire communities over many years, or even lifetimes. The idea of creating these self-contained environments brings us closer to the vision of space colonies like O'Neill cylinders or Stanford Torrey, massive rotating structures that simulate gravity through centrifugal force. These colonies would house thousands of people in sprawling, Earth-like environments complete with artificial skies, rivers, and forests. By rotating the structure, they could generate gravity similar to that of Earth, mitigating the health issues associated with living in low-gravity environments such as those on the Moon or Mars. Inside, these space colonies would feel familiar: green parks, bustling cities, and self-sustaining agricultural systems. In many ways, life in such colonies might resemble life on Earth, though with key differences brought on by the challenges and opportunities unique to space. Beyond the technical challenges of building these habitats, there are the social and cultural aspects of creating entirely new worlds. How will people govern themselves in space? Will Earth's political systems translate to new environments? Or will space settlers create novel forms of governance tailored to the realities of life beyond Earth? Many scientists, visionaries, and space advocates argue that the frontier nature of space will foster new ways of thinking about society, governance, and human cooperation. Space offers the chance to rethink economic systems as well. Unlike Earth, where resources are finite and often contested, space contains vast amounts of untapped resources. Asteroids, for example, are rich in metals like iron, nickel, and even precious elements such as gold and platinum. The potential for asteroid mining could not only fuel the construction of space habitats, but also provide the raw materials for a booming space economy. Entire industries could emerge in orbit and beyond, from manufacturing to tourism, as we develop the technology to access and utilize these resources efficiently. Already, private companies like SpaceX, Blue Origin, and others are laying the groundwork for commercial space travel. Space tourism, once the realm of science fiction, is becoming a reality with suborbital flights now available for wealthy passengers, and plans for more ambitious missions are on the horizon. As costs continue to fall, the idea of a middle-class family vacationing in low Earth orbit may no longer be a fantasy, but a practical option in the not-too-distant future. Eventually, some of these tourists may decide not to return to Earth, choosing instead to settle in space habitats or colonies on the Moon or Mars. With the establishment of permanent space settlements, humanity will have to adapt not only technologically, but biologically. One of the most fascinating and speculative frontiers in this area is human enhancement. Using genetic engineering, biotechnology, and even cybernetic augmentation to modify humans for life in space. For example, engineers might develop ways to enhance human resistance to radiation, a major concern for space travelers beyond the protection of Earth's atmosphere. Similarly, future space settlers might benefit from enhancements that allow them to tolerate low-gravity environments better or to thrive in reduced oxygen conditions. The idea of altering the human body for space raises profound ethical questions. Should we modify ourselves to adapt to space, or should we focus on building environments that mimic Earth as closely as possible? While genetic engineering and cybernetics could dramatically improve our ability to live in space, they also challenge our traditional ideas of what it means to be human. As we explore these possibilities, society will need to engage in deep discussions about the balance between maintaining our humanity and evolving to meet the demands of a spacefaring future. In parallel to these technological advancements, there is also the growing potential of artificial intelligence, AI, to support and guide our journey into the cosmos. AI could become the key to managing the complex systems required for space habitats to function. From regulating life support to optimizing resource extraction from asteroids or other celestial bodies, AI could handle tasks that would be overwhelming for human operators. More advanced AI systems might even take on leadership roles within space colonies, helping to solve governance challenges or maintain order in these new societies. Moreover, AI could serve as a bridge between human settlers and the alien environments they inhabit. Robots powered by AI could be sent to the most inhospitable places in the solar system, such as the surface of Venus or the icy moons of Jupiter and Saturn, conducting research and preparing these locations for future human exploration. With advancements in robotics and machine learning, these AI systems could act as autonomous explorers, sending back data to Earth while making real-time decisions based on the conditions they encounter. At the same time, AI's role in space exploration brings up crucial questions about autonomy, trust, and the boundaries between human and machine. If AI becomes advanced enough to handle critical tasks on its own, will humans remain in control, or will we find ourselves increasingly reliant on machines to manage our space colonies? These questions mirror broader debates about AI's role on Earth, but they take on new urgency in the context of space, where the stakes are higher and the environment's far more dangerous. As we expand deeper into space, the ethical dimensions of exploration will also grow more complex. One of the most critical questions we must grapple with is how we interact with other worlds. The idea of planetary protection, the principle of avoiding contamination of other planets with Earth-based life, will become even more relevant as we explore Mars, Europa, and other potentially habitable worlds. If we discover microbial life on Mars, for instance, should we prioritize its preservation over human colonization? Would we have the right to alter or terraform a world that already hosts native life forms, however simple they may be? Our responsibility extends beyond living organisms. Even planets and moons without life hold immense scientific value, containing clues to the early history of the solar system and the origins of life itself. As we begin to mine asteroids or colonize planets, we must balance our desire for resources with the need to preserve these worlds for future generations of scientists and explorers. This responsibility is global, transcending national boundaries, and will require new international frameworks and treaties to ensure that space is explored ethically and sustainably. In addition to these ethical questions, the prospect of discovering extraterrestrial life remains one of the most exciting possibilities of space exploration. Whether we find microbial life beneath the icy crust of Europa or detect signals from an intelligent civilization in a distant star system, such a discovery would change everything. It would force us to reconsider our place in the universe and challenge many of our fundamental assumptions about life, intelligence, and consciousness. If we do find intelligent extraterrestrial life, the encounter would raise profound questions about communication and diplomacy. How do we make contact with a species that may have evolved in ways entirely different from our own? What common ground would we find with beings that might not share our biology, our senses, or our concept of reality? Would we be able to understand their language, their technology, or their culture? These questions are not just theoretical. They are practical challenges that scientists, linguists, and diplomats may one day have to solve. Even if we never find extraterrestrial civilizations, the search itself has already changed us. It has pushed us to look outward, beyond the confines of Earth, and to contemplate the possibility that we are not alone. The search for life beyond Earth is not just about discovering new species. It is about expanding our understanding of what life is and what it could be. It forces us to think about our own civilization from a broader perspective, to consider the long-term survival of our species, and to ask what kind of future we want to build for ourselves in the universe. As we look toward the stars, we are reminded that space exploration is not just a technical or scientific endeavor. It is a deeply human one. It taps into our oldest instincts, our curiosity, our desire to explore, our drive to build and create. Space represents the ultimate challenge, the final frontier, and the greatest opportunity for growth and discovery that humanity has ever known. In the centuries to come, space exploration will shape the destiny of humanity. We may establish thriving colonies on Mars and other planets, build vast habitats in orbit, or even send human explorers to distant star systems. We may find new forms of life, new ways of living, and new ways of thinking about our place in the cosmos. The universe is unimaginably vast, and we are only at the very beginning of our journey. But one thing is certain: as we venture out into the stars, we will carry with us the spirit of exploration, innovation, and wonder that has defined humanity since the dawn of time. The future of space is not just about discovering new worlds. It is about discovering new possibilities within ourselves. The stars await, and the adventure is just beginning. As we continue our journey into the great expanse of space, the vast unknown not only challenges our scientific understanding, but also forces us to reimagine what the future of humanity could look like in the cosmos. Every new leap into space brings us closer to a time when the exploration and colonization of planets, moons, and even the furthest reaches of the galaxy become part of the fabric of human existence. This evolution will not simply be technological, but cultural, social, and philosophical. It will change the way we think about our species, our planet, and our relationship with the universe. One of the most pressing challenges in the immediate future of space exploration is the creation of sustainable environments for long-term human habitation. On Earth, we are used to taking breathable air, fresh water, and fertile soil for granted. But in space, every resource must be managed with extreme precision. The development of closed-loop life support systems, where air, water, and waste are continuously recycled, is critical for survival in space. On Mars, the Moon, or in space habitats, such systems will ensure that settlers can live without constantly depending on resupply missions from Earth. This technology is already being tested on the International Space Station, where astronauts recycle up to 90% of their water. Future iterations will need to be even more efficient, and they will likely incorporate advanced biotechnology, perhaps even synthetic biology, to optimize the recycling of organic material. Beyond life support, creating a thriving ecosystem in space means addressing the psychological and social needs of humans. Space is a harsh and isolating environment, and the mental well-being of settlers will be just as important as their physical survival. In the early stages of colonization, space travelers will live in tightly confined quarters, with limited social interaction and long periods of isolation from Earth. Research on how isolation affects the human psyche, whether in Antarctic research stations, submarines, or space missions, provides important insights into how future settlers can maintain their mental health. Virtual reality (VR) may play a critical role in helping colonists cope with the isolation of space. VR technology could allow people to immerse themselves in realistic simulations of Earth environments, such as forests, oceans, or familiar urban landscapes, helping them to alleviate feelings of homesickness or claustrophobia. As space colonies grow and populations increase, the social dynamics of these new communities will become increasingly complex. The founding of colonies on Mars, the Moon, or in artificial habitats will require new forms of governance, law, and economics. Will space colonies be governed by Earth-based laws, or will they develop their own systems of governance? Will the concept of nation-states survive in space, or will new political structures emerge? Some theorists suggest that space colonies could adopt more decentralized, cooperative models of governance, perhaps influenced by the frontier spirit that shaped early human settlements on Earth. These new societies may be shaped by a shared sense of purpose, survival in a challenging environment, or they may eventually diverge from Earth-based norms and develop entirely unique cultures and identities. Economically, space colonization opens the door to a new era of resource extraction and manufacturing. Asteroids and other celestial bodies contain vast quantities of valuable materials, such as metals, minerals, and water. For example, a single metal-rich asteroid could contain more platinum than has ever been mined on Earth. These resources could be used to fuel the space economy, providing the raw materials for building new habitats, spacecraft, and infrastructure. Companies like Planetary Resources and Deep Space Industries are already developing the technology to mine asteroids, and this industry could one day drive economic growth not just in space, but on Earth as well. In addition to mining, space offers the potential for large-scale manufacturing using 3D printing and in-situ resource utilization, ISRU. ISRU involves using local materials, whether lunar regolith, Martian soil, or asteroid metals, to build structures and produce goods on-site, rather than transporting everything from Earth. This could revolutionize space settlement by dramatically reducing costs and making colonies more self-sufficient. On Mars, for instance, ISRU could allow settlers to build habitats, create tools, and even produce rocket fuel from the planet's abundant carbon dioxide and water ice. By using the resources already present in space, we can create a sustainable infrastructure that supports long-term human expansion beyond Earth. As we develop the technology to build and sustain colonies in space, we must also confront the ethical implications of our actions. Space is a pristine environment, untouched by the pollution and environmental degradation that humans have inflicted on Earth. How we interact with space, whether we treat it as a resource to be exploited or a place to be preserved, will define our legacy as a spacefaring species. Many scientists and ethicists argue for a cautious approach, one that prioritizes planetary protection and the preservation of space environments for future generations. For example, if we discover life on Mars or another celestial body, even microbial life, should we prioritize the preservation of that life over our own colonization efforts? These are questions that will need to be addressed as space exploration advances. In parallel with these practical and ethical concerns, space exploration will inevitably reshape human culture. Just as the age of exploration on Earth led to the exchange of ideas, technologies, and cultures across continents, the era of space exploration will foster the creation of new cultural identities and artistic expressions. The experience of living in space, with its unique physical and psychological challenges, will inspire new forms of art, literature, music, and philosophy. The Martian sunset, with its pink and blue hues, or the rings of Saturn as seen from its moons, could become iconic symbols in the artwork of future spacefaring societies. The arts will play a critical role in shaping how we understand our place in the universe. They will help us process the emotional and existential aspects of living in space, the isolation, the wonder, the fear, and the hope. In space, We will be forced to confront fundamental questions about life, humanity, and the universe. What does it mean to be human in an environment where we are so far from our origins? How do we create meaning in a world where Earth is no longer the center of our existence? These questions will drive artistic and philosophical exploration as we seek to find new ways of expressing the experience of life among the stars. In addition to the arts, the expansion of humanity into space will transform our understanding of science and discovery. As we explore new worlds, we will encounter phenomena that challenge our existing knowledge of physics, biology, and chemistry. The discovery of life elsewhere in the universe, whether microbial life on Mars or complex life forms on exoplanets, would be one of the most profound scientific breakthroughs in history. Such a discovery would force us to rethink our understanding of biology and the conditions necessary for life. It might even lead to the development of new branches of science, focused on the study of alien ecosystems and biochemistries. Our scientific understanding of the universe will also be transformed by the discovery of new forms of energy and matter. The search for dark matter and dark energy, which make up the vast majority of the universe's mass and energy but remain poorly understood, could lead to groundbreaking discoveries in fundamental physics. These discoveries could unlock new technologies, such as faster-than-light travel, or even provide insights into the origins of the universe itself. The mysteries of black holes, neutron stars, and the fabric of space-time will continue to drive scientific exploration, pushing the boundaries of human knowledge. As we look to the future, it is clear that space exploration is not just a technical challenge. It is a profound human endeavor, one that will shape the trajectory of our species for millennia to come. It will require us to develop new technologies, new ways of living, and new ways of thinking about the universe and our place within it. It will test our ability to cooperate, innovate, and adapt to new environments. And it will push us to imagine futures that are beyond anything we can currently conceive. In the coming centuries, humanity may spread across the solar system, establishing colonies on Mars, the Moon, and the moons of Jupiter and Saturn. We may build massive space habitats that orbit the Earth or exist in the asteroid belt. We may even venture beyond our solar system, sending explorers to distant star systems and discovering entirely new worlds. Along the way, we will encounter challenges and opportunities that we cannot yet predict, but one thing is certain: the future of humanity is in the stars. As we stand on the edge of this new era, we are reminded of the words of Carl Sagan, who once said, "Somewhere, something incredible is waiting to be known." The universe is vast, mysterious, and full of wonders that we have only just begun to explore. Our journey into space is just beginning, and the possibilities are as endless as the stars themselves. The adventure awaits, and humanity's destiny is written in the cosmos. As we move further into the depths of space exploration, the horizons of possibility expand in ways that are both exhilarating and humbling. The next phase of humanity's venture into the cosmos will not only be about conquering new frontiers, but also about adapting and evolving to live in the most challenging environments ever encountered. We are on the verge of transforming space from a destination for discovery into a place where people can live, work, and flourish, creating entirely new societies that are self-sustaining and innovative, while deeply intertwined with the unknown forces of the universe. One of the first significant steps towards this future will be the establishment of permanent human colonies on Mars. While Mars has been the subject of numerous robotic missions and is set to be the destination for the first crewed missions in the coming decades, the long-term vision is to create permanent, self-sustaining settlements on the Red Planet. The process of turning Mars into a habitable world will involve terraforming on a small scale at first, building enclosed habitats where humans can live and work, protected from the harsh Martian environment. These early Martian habitats will likely be constructed using materials sourced directly from Mars itself, such as regolith for 3D printed buildings or structures buried underground to shield inhabitants from cosmic radiation. Advances in technologies like bioreactors, hydroponic farming, and vertical agriculture will enable colonists to grow their food inside these habitats. This will be critical for survival, as the vast distance between Earth and Mars makes frequent resupply missions impractical. The goal is to develop Mars into a self-sufficient colony where humans can live for extended periods without relying on Earth for basic necessities. As this Martian society grows, it will face unique challenges that will shape its cultural and political identity. The physical isolation from Earth, combined with the psychological effects of living in a confined environment on an alien planet, will require careful planning to maintain social cohesion. Mars could become a hub of technological and societal experimentation, where new forms of governance, economics, and community building emerge. Settlers may develop a stronger sense of independence from Earth over time, potentially leading to discussions about Martian autonomy and even the possibility of Martian sovereignty. The settlement of Mars will likely be followed by further colonization efforts elsewhere in the solar system. The moons of Jupiter and Saturn offer tantalizing possibilities for human exploration and colonization. Europa, with its vast subsurface ocean, is one of the most promising candidates for the discovery of extraterrestrial life within our solar system. Future missions to Europa could send submarines to explore its icy depths, searching for microbial life in its dark, liquid oceans. If life is discovered there, it could transform our understanding of biology and the conditions necessary for life to exist, giving us new clues about how life might develop on exoplanets. Ganymede and Callisto, two of Jupiter's largest moons, also present interesting opportunities for colonization. Ganymede has a magnetic field, which could offer some protection from cosmic radiation, while Callisto's distance from Jupiter's radiation belt makes it a safer destination for human explorers. Colonies on these moons could be stepping stones for future missions to the outer solar system, as well as scientific outposts for studying the gas giants and their moons in greater detail. Saturn's moon Titan is another intriguing candidate for human settlement. With its thick atmosphere and lakes of liquid methane and ethane, Titan presents a world that is both familiar and alien. The atmosphere is dense enough that humans could potentially walk on Titan's surface without the need for a pressurized suit, though they would still need oxygen and protection from the extreme cold. Settlements on Titan would rely on harnessing local resources, such as hydrocarbons from its methane lakes, to generate energy and build infrastructure. Over time, Titan could become a hub for research and exploration of the outer solar system, as well as a unique location for studying planetary processes that differ significantly from those on Earth. While the solar system presents a wealth of opportunities for exploration and colonization, the ultimate goal for humanity may lie beyond our own star system. The dream of interstellar travel, long the domain of science fiction, is now being seriously considered by scientists and engineers. Although the distances between stars are staggering, Proxima Centauri, the nearest star to our Sun, is 4.24 light-years away. There are several concepts that could one day make interstellar travel possible. One of the most promising ideas is the use of light sails, propelled by powerful laser beams from Earth. These light sails could carry small, lightweight spacecraft at a significant fraction of the speed of light, allowing them to reach nearby star systems within a few decades. The Breakthrough Starshot initiative is currently working on developing this technology, with the goal of sending tiny robotic probes to Alpha Centauri. While human travel to other star systems is still far in the future, these early steps toward interstellar exploration could pave the way for more ambitious missions. In addition to light sails, other advanced propulsion concepts, such as nuclear fusion or antimatter drives, could one day enable human crews to travel to distant star systems. These propulsion systems would provide the energy needed to overcome the immense distances between stars, potentially reducing travel times to decades or even years. However, building and testing these technologies will require breakthroughs in physics, engineering, and energy production, which are likely many decades away. If we do manage to reach other star systems, the search for habitable exoplanets will be a top priority. Already, astronomers have discovered thousands of exoplanets, some of which are located in the habitable zones of their parent stars, where conditions might be right for liquid water, and therefore life, to exist. One of the most promising of these is Proxima b, an Earth-sized planet orbiting Proxima Centauri, the nearest star to our Sun. Although much remains unknown about Proxima b's atmosphere and surface conditions, its location in the habitable zone makes it a prime target for future exploration. As we begin to explore these distant worlds, We will face new ethical questions about how to approach planets that could potentially harbor life. If we discover microbial life on an exoplanet, should we attempt to colonize it, or should we preserve it for scientific study? And if we encounter intelligent extraterrestrial civilizations, how should we approach them? These questions will require careful consideration, as the consequences of contact with alien life, whether simple microbes or advanced beings, could reshape the course of human history. The discovery of extraterrestrial life, in any form, would challenge our understanding of biology, evolution, and even the nature of life itself. It would force us to reconsider our place in the universe and the uniqueness of life on Earth. But even if we never find life elsewhere, the act of exploring the universe will still deepen our connection to it. Every new world we discover, every star system we explore, will expand our understanding of the cosmos and our role within it. As we look beyond the stars and contemplate the farthest reaches of the universe, we are reminded that space exploration is not just about expanding our physical boundaries. It is about expanding the boundaries of human knowledge, imagination, and potential. The technology we develop for space exploration, whether it's advanced propulsion systems, life support technologies, or new forms of artificial intelligence, will have far-reaching effects on life on Earth. Space exploration has always been a catalyst for innovation, driving new technologies that improve our lives in ways we couldn't have imagined. Moreover, the exploration of space has the power to unite humanity in a shared sense of purpose. In a world often divided by politics, borders, and conflict, the vastness of space offers a reminder of our common humanity. We are all part of the same fragile planet, orbiting a star in a small corner of a vast galaxy, itself only one of trillions in the universe. The challenges we face, both on Earth and in space, will require collaboration, cooperation, and a shared vision for the future. The journey ahead is filled with uncertainty, but it is also filled with incredible potential. Whether we are building cities on Mars, exploring the icy moons of the outer solar system, or traveling to distant star systems, the future of space exploration promises to be an era of discovery, innovation, and growth unlike any humanity has ever experienced. As we stand at the dawn of this new age, we must embrace the spirit of exploration that has driven us for millennia. The universe is vast and full of wonders, and we are only just beginning to unlock its secrets. The stars are waiting, and the journey to reach them is not only a scientific and technological adventure, it is a deeply human one. It is about pushing the limits of what is possible, seeking out new horizons, and understanding the universe and our place within it in ways that will forever transform who we are as a species. The future belongs to the explorers, the dreamers, and the visionaries who dare to look up and imagine what lies beyond. Our journey into the cosmos is just beginning, and the possibilities are as infinite as the universe itself. As we continue to gaze toward the stars and chart our path forward into the cosmos, the vision of a spacefaring civilization grows clearer. Each step we take brings us closer to transforming the dream of interplanetary living into a reality. And with that transformation comes not only technological innovation, but also profound changes in how we define life, community, and our place in the universe. One of the most transformative aspects of the future will be the rise of interplanetary economies. As humans establish permanent colonies on the Moon, Mars, and beyond, the need for trade and industry between worlds will evolve, creating a space economy that operates on a scale previously unimaginable. This economy will be driven by the need for resources such as water, minerals, metals, and even energy. Water, often considered the most valuable resource in space, will become the oil of the cosmos. Whether harvested from lunar ice, Martian subsurface reserves, or from asteroids, water will be essential not just for sustaining human life, but for producing fuel in the form of hydrogen and oxygen through electrolysis. Asteroid mining will play a critical role in this new economy. Asteroids, rich in metals like iron, nickel, and cobalt, as well as rarer materials like platinum group metals, offer a vast untapped resource base. Mining these asteroids will be key to supplying the materials needed for constructing space habitats, building spacecraft, and developing the infrastructure for space colonies. Moreover, Space mining could eventually become so lucrative that it fuels Earth's economy as well, reducing the need for environmentally damaging mining practices on our home planet. In the near term, companies like SpaceX, Blue Origin, and others are working to create reusable spacecraft, which will dramatically lower the cost of launching materials and people into space. But looking further ahead, the construction of space-based manufacturing facilities will mark the next leap in economic expansion. These factories could use resources harvested in space to create everything from electronics to entire space stations, bypassing the need to launch raw materials from Earth. Such manufacturing would be especially valuable for large-scale projects like space habitats or interplanetary spacecraft that require substantial resources and energy to build. Beyond mining and manufacturing, energy production will be a cornerstone of interplanetary societies. Solar energy, which is abundant and reliable in space, will likely power most space-based infrastructure. Satellites equipped with massive solar arrays could beam energy back to Earth or to other planets using microwave or laser technology. These solar power stations, positioned in geostationary orbits or on the Moon, would provide clean, nearly limitless energy to support growing space settlements. In more distant regions of the solar system, where sunlight is weaker, nuclear fusion reactors could become the primary energy source, offering a compact and powerful solution to energy needs. As space industries grow and interplanetary trade routes are established, humanity will begin to form a new kind of global economy, one that is no longer limited to a single planet. Trade networks could emerge between Earth, Mars, and space stations in orbit or on the Moon. The transportation of goods and materials across vast distances will require not only advanced propulsion technologies, but also new logistical systems to manage supply chains that stretch across millions of kilometers. These systems will include autonomous spacecraft and cargo drones capable of navigating space routes and making deliveries between planets and space stations with minimal human intervention. In parallel with the development of an interplanetary economy, we will see the rise of interplanetary governance. As human populations grow beyond Earth, the need for new political systems to manage these colonies will become increasingly urgent. Early space colonies may be governed by Earth-based institutions, such as national space agencies or international coalitions. But as they become more self-sufficient, there will likely be calls for greater autonomy. Mars, with its growing population and unique challenges, could become the first planet to declare independence from Earth, establishing its own government and laws. The development of interplanetary governance will not be without challenges. Colonies on Mars, the Moon, or in orbiting space habitats will be physically isolated from Earth, making direct oversight difficult. Communications delays, up to 20 minutes one way between Earth and Mars, will necessitate a high degree of local control. These colonies will need the ability to make decisions quickly and independently, whether it be in response to a crisis or in the day-to-day management of resources and infrastructure. The nature of governance in space may differ significantly from what we are familiar with on Earth. The unique challenges of space life, such as the need for cooperation, resource management, and survival in extreme conditions, could inspire new forms of democratic governance, or perhaps even cooperative or decentralized systems that emphasize collective decision-making and sustainability. As colonies grow and evolve, they could develop their own distinct political and cultural identities, leading to the emergence of entirely new societies. Just as governance will evolve, so too will the social and cultural aspects of life in space. The experience of living on another planet will fundamentally change the way humans think about themselves and their place in the universe. Martian settlers, for example, may develop a shared identity that is distinct from Earth, shaped by the harsh realities of life on Mars and the challenges of building a new world from scratch. These settlers will likely form tight-knit communities, bound together by their shared experience and the need to cooperate for survival. The arts, literature, and philosophy of spacefaring societies will reflect these new realities. The unique beauty of alien landscapes, the vast red deserts of Mars, the icy plains of Europa, the methane lakes of Titan, will inspire new forms of artistic expression. The isolation of living far from Earth, combined with the psychological and emotional challenges of life in space, will drive new genres of storytelling, music, and visual art that explore themes of isolation, exploration, and the search for meaning in the universe. As human culture expands into space, so too will our spiritual and philosophical outlooks. For millennia, humans have looked to the stars as a source of wonder, mystery, and inspiration. As we begin to explore the cosmos firsthand, we may find ourselves asking deeper questions about the nature of existence, consciousness, and our relationship to the universe. The experience of standing on the surface of Mars, gazing up at a night sky filled with stars and distant planets, could provoke profound shifts in how we understand ourselves, our purpose, and our place in the cosmos. These philosophical questions will be amplified if we discover extraterrestrial life, whether it be microbial organisms on Mars or intelligent civilizations in distant star systems. The discovery of life beyond Earth would challenge our most fundamental assumptions about biology, evolution, and consciousness. It would force us to reconsider our definitions of life and intelligence, and it would raise profound ethical questions about how we interact with these life forms. Would we have the right to colonize or alter a planet that harbors alien life, even if that life is microbial? How would we approach contact with an intelligent species that is vastly different from us, both biologically and culturally? Even if we never encounter extraterrestrial civilizations, the discovery of life elsewhere in the universe, whether simple or complex, would be one of the most transformative moments in human history. It would fundamentally alter our understanding of life's potential in the universe and our place within it. The knowledge that life exists elsewhere, even in the form of simple organisms, would inspire new scientific inquiries and philosophical debates about the origins of life, the nature of intelligence, and the possibilities of other forms of consciousness. The discovery of life beyond Earth would also have significant implications for religion and spirituality. Throughout human history, religious traditions have grappled with the meaning of the cosmos and humanity's place within it. The knowledge that life exists on other planets could challenge or deepen these traditions, leading to new interpretations of ancient teachings and the emergence of new spiritual frameworks that reflect humanity's expanded understanding of the universe. As we venture further into space, we will also need to confront the ethical and environmental challenges of exploration and colonization. Space is a vast and largely untouched frontier, and how we choose to interact with it will have long-lasting consequences. The concept of planetary protection, which aims to prevent contamination of other worlds by Earth-based life, will become even more critical as we explore potentially habitable planets and moons. Ensuring that we do not inadvertently introduce Earth microbes to Mars, Europa, or other celestial bodies is essential for preserving these environments for scientific study and for protecting any indigenous life that may exist. Moreover, as we begin to mine asteroids and settle other planets, we will need to develop sustainable practices that minimize environmental damage. The experience of environmental degradation on Earth should serve as a cautionary tale for how we approach the exploitation of space resources. We have the opportunity to build a spacefaring civilization that learns from Earth's mistakes, prioritizing sustainability, cooperation, and stewardship over short-term gains. The choices we make now will shape the future of space exploration and the legacy we leave for generations to come. Ultimately, the future of space exploration is about more than just technology and discovery. It is about the evolution of humanity itself. As we push beyond the boundaries of our planet, we will be forced to confront new challenges, new possibilities, and new ways of thinking. We will encounter the unknown, both in the universe and within ourselves, and we will be transformed by the experience. The stars are calling us, and as we take our first steps into the cosmos, we are embarking on a journey that will reshape the future of humanity in ways we can scarcely imagine. The universe is vast, full of mysteries, and filled with opportunities for discovery, growth, and connection. As we venture into this new frontier, we carry with us not just the tools of science and technology, but the hopes, dreams, and aspirations of all humankind. The future of space is the future of humanity, and the adventure has only just begun. As we continue to look ahead into the ever-expanding future of space exploration and humanity's place in the cosmos, one concept that stands out is the potential for space not only to serve as a new domain for exploration, but as a canvas for the most imaginative aspects of human creativity. Space may become the birthplace of entirely new ways of life, culture, and civilization, transforming our relationship to the universe and ourselves in ways we are just beginning to comprehend. A major leap that will define the next stage of human expansion into the cosmos is the eventual emergence of space megastructures, massive artificial habitats and stations capable of sustaining large populations over long periods, potentially indefinitely. These megastructures, which have been the focus of both scientific theorization and science fiction, could range from rotating space stations designed to simulate gravity through centrifugal force to Dyson spheres or swarms that collect energy directly from stars. While these concepts may seem fantastical today, the rapid pace of technological advancement could one day bring them within reach. One such concept, the O'Neill cylinder, is an artificial habitat in the shape of a vast rotating cylinder where entire ecosystems, complete with cities, rivers, forests, and farmland, could be housed. By rotating the structure, the cylinder would generate artificial gravity on its inner surface, creating an Earth-like environment where large human populations could live comfortably. The scale of such a habitat could vary, but some proposals suggest that these cylinders could be several kilometers long and large enough to support tens or hundreds of thousands of people. These spaceborne cities would represent not only an engineering feat, but also a major step in human self-sufficiency beyond Earth. They would be powered by solar energy and would recycle air, water, and organic materials to maintain a closed-loop ecosystem, ensuring that they could operate independently for generations. The construction of such megastructures would open up new possibilities for human settlement in space. Instead of being confined to the surfaces of planets like Mars or the Moon, humanity could thrive in orbit around Earth, in the asteroid belt, or even in deep space. These habitats could be used as way stations for long-term missions, as spaceports for interstellar travel, or as self-contained societies completely detached from Earth. Entire civilizations could develop within these artificial worlds, with their own customs, laws, and identities. While the technical challenges of building space megastructures are immense, we are already laying the groundwork with current advances in robotics, autonomous construction, and material science. 3D printing technology, for example, is being tested to create structures using local materials on the Moon or Mars, and similar techniques could be used to construct megastructures in space. Robots capable of operating in zero-gravity and hostile environments will play a key role in assembling these habitats, working around the clock to build vast structures far beyond the capabilities of human labor. Beyond space megastructures, the concept of a Dyson sphere or Dyson swarm represents the next step in humanity's quest for energy and sustainability in space. A Dyson sphere, named after physicist Freeman Dyson, is a hypothetical megastructure that would completely surround a star, capturing nearly all of its energy output to power advanced civilizations. While constructing a solid shell around a star might be technologically impossible, a more practical version, a Dyson swarm, could consist of a vast array of satellites or solar collectors that orbit the star, harvesting its energy. Such a structure would provide an almost limitless source of power, enabling civilizations to grow exponentially without being constrained by the energy limitations of planets or even solar systems. The ability to harness the energy of an entire star would push a civilization into what is known as a Type II civilization on the Kardashev scale, a hypothetical framework that measures a civilization's technological advancement based on its energy consumption. Earth today is considered a Type I civilization, harnessing energy from its planet, but a Type II civilization would be capable of harnessing the full energy output of its star. Beyond that, a Type III civilization would be able to harness the energy of an entire galaxy. The implications of achieving Type II or Type III status are profound. With virtually limitless energy, humanity could expand across star systems, colonizing planets, building more megastructures, and even beginning to manipulate the very fabric of space-time. The barriers to interstellar travel, such as the immense distances between stars, could be overcome with advanced propulsion systems powered by the energy of stars themselves. One concept that might become viable with such immense energy resources is the warp drive, a theoretical propulsion system that would allow spacecraft to travel faster than the speed of light by warping space-time around them. While this idea remains speculative, scientists like Miguel Alcubierre have proposed theoretical models that suggest it could be possible within the laws of physics, provided that we can generate the required energy. A warp drive could make interstellar travel feasible within human lifetimes, opening up the possibility of exploring distant star systems and discovering other habitable worlds or even intelligent civilizations. As we move toward becoming a multiplanetary and even interstellar species, the question of human adaptation to space will become increasingly important. Space is an environment that is hostile to life as we know it. Extreme temperatures, radiation, microgravity, and the absence of breathable air all pose serious challenges to human health and survival. While we have developed technologies to protect astronauts from these dangers on short-term missions, long-term habitation in space will require more radical solutions. One of the most promising areas of research is in genetic engineering and biotechnology. Advances in CRISPR and other gene editing technologies could allow us to modify human biology to better cope with the challenges of space. For example, humans could be genetically modified to be more resistant to radiation or to thrive in low-gravity environments. These modifications could enhance muscle and bone density, improve oxygen efficiency, or even allow humans to hibernate during long space journeys. While such genetic modifications raise ethical questions, they could be essential for ensuring the long-term survival of humanity in space. Another possibility is the development of cyborg technology, the integration of artificial components with the human body. Future spacefarers might have artificial organs that allow them to breathe in thin or toxic atmospheres, or bionic limbs that are better suited to the rigors of space exploration. Cyborg technology could also enhance human intelligence by connecting the brain directly to advanced computers, allowing people to process vast amounts of information or control machines with their thoughts. This merging of biology and technology could give rise to a new form of human existence, one that is not constrained by the limitations of the biological body. As humans adapt physically and mentally to life in space, we may also see the emergence of entirely new forms of consciousness. The integration of artificial intelligence with the human mind could lead to the creation of augmented humans or even digital consciousness. In the future, it might be possible to upload human consciousness into a digital format, allowing people to exist indefinitely as digital beings, free from the constraints of the physical body. These digital humans could inhabit virtual worlds, explore the universe as part of a spacecraft's AI system, or interact with physical reality through robotic avatars. The emergence of digital consciousness could blur the line between human and machine, raising profound philosophical questions about identity, consciousness, and what it means to be human. If our consciousness can be copied or transferred into machines, are we still the same person? Could multiple copies of the same consciousness exist simultaneously? And what would that mean for individuality and personal identity? These questions, which once seemed like science fiction, may become real dilemmas for future generations. The development of digital consciousness could also play a role in overcoming the challenges of interstellar travel. Human life, in its current biological form, is ill-suited for the vast distances between stars. Even with advanced propulsion technologies, a journey to a distant star system could take decades or centuries. However, a digital consciousness could exist indefinitely without the need for food, water, or oxygen. It could be sent on long journeys across the galaxy, exploring new worlds and sending information back to Earth or other colonies. This would allow humanity to explore the farthest reaches of the universe without being constrained by the limitations of the biological body. In parallel with the development of advanced technology, the ethical and philosophical implications of space exploration will continue to shape the future of humanity in space. As we establish colonies on other planets, mine asteroids, and harness the energy of stars, we will need to ensure that our actions are guided by principles of sustainability, stewardship, and respect for the environments we encounter. The mistakes we have made on Earth, pollution, environmental degradation, resource depletion, must not be repeated in space. Instead, we have the opportunity to build a spacefaring civilization that prioritizes long-term sustainability, cooperation, and ethical responsibility. The future of space exploration is not just about expanding human presence across the cosmos. It is about redefining what it means to be human in a universe that is far larger, stranger, and more complex than we have ever imagined. As we venture deeper into space, we will encounter challenges that test the limits of our creativity, intelligence, and adaptability. But we will also discover new possibilities for life, consciousness, and civilization that transcend the boundaries of our current understanding. The journey ahead is filled with unknowns, but it is also filled with promise. As we push beyond the confines of our planet and into the vastness of space, we are embarking on the greatest adventure in human history, one that will shape the future of our species for millennia to come. The stars are calling, and as we take our first steps into the cosmos, we carry with us the hope, ambition, and curiosity that have always driven humanity to explore the unknown. As we continue to explore the boundless frontiers of space, the next logical phase of human expansion brings us closer to creating a truly interstellar civilization, one capable of thriving both within our solar system and beyond. This vision of the future goes far beyond simply colonizing planets or constructing megastructures. It involves humanity fundamentally reshaping its relationship with the universe. In this new era, the lines between technology, biology, culture, and exploration will blur as we develop new ways of living and interacting with both the cosmos and each other. One of the first profound changes in this era of space expansion will be the creation of interplanetary societies. As permanent colonies are established on the Moon, Mars, and in orbiting habitats, the need for cohesive social structures will become paramount. These societies will face challenges unlike anything humanity has previously encountered, from the need to manage life support systems to the psychological effects of living so far from Earth. Over time, these off-world societies will develop distinct cultures, with unique customs, traditions, and values that reflect their environments and the experiences of their inhabitants. Life on Mars, for instance, will be radically different from life on Earth. Martian settlers will have to adapt to the planet's lower gravity, harsh climate, and the constant necessity of living within enclosed, artificial environments. These challenges will shape how Martians view themselves and their place in the universe. Over generations, Martians may begin to see themselves not just as Earthlings living on another planet, but as members of a new and distinct human society. This could give rise to new philosophies, ideologies, and perhaps even political movements centered around Martian independence and self-governance. Similarly, lunar colonies will face their own unique challenges. The Moon's proximity to Earth means that lunar settlers will have more regular communication and interaction with their home planet than Martians. But the Moon's lack of atmosphere and extreme temperatures will make life there just as challenging. Lunar colonies may become hubs for scientific research, mining, and space tourism, as well as waypoints for missions deeper into the solar system. The development of a lunar economy, based on resource extraction and energy production, could eventually make the Moon a vital part of the broader space economy. As these interplanetary societies grow, they will also need to address the question of how to govern themselves. Will these colonies be extensions of Earth-based nations, or will they evolve into independent entities with their own political systems? The unique conditions of space may inspire new forms of governance that emphasize collective decision-making, sustainability, and cooperation, as survival in space will require a high degree of collaboration. Some futurists envision that space colonies could become laboratories for new political experiments, testing out systems of governance that are more decentralized or even post-scarcity, as the abundance of resources in space could change the dynamics of economies and power. In addition to the development of new social and political structures, space exploration will also spark an unprecedented expansion of human creativity and culture. As we move beyond Earth, the experience of living in space will inspire new forms of art, music, literature, and philosophy. Space will provide a backdrop for artistic expressions that reflect the isolation, wonder, and awe of living among the stars. Artists will draw inspiration from the landscapes of alien worlds, the red deserts of Mars, the icy expanses of Europa, the endless darkness of deep space. Music, too, will evolve in space, with new genres emerging that reflect the sounds and rhythms of space environments. The absence of air in space means that sound cannot travel as it does on Earth, but within space habitats, artificial environments will provide opportunities for musicians to experiment with new acoustics and sonic textures. Composers may use the low-gravity environments of space stations to create music that interacts with movement in ways that would be impossible on Earth. Visual artists, meanwhile, will be inspired by the alien beauty of planets, moons, and nebulae, using new mediums and techniques to capture the essence of these otherworldly environments. Space exploration will also push the boundaries of philosophy and spirituality. As we venture further into the universe, humans will inevitably confront deeper questions about the nature of existence, the meaning of life, and our place in the cosmos. The experience of living on another planet, where the familiar sights and sounds of Earth are absent, will challenge long-held assumptions about identity and belonging. Philosophers may grapple with questions of human purpose in an infinite universe, exploring new ways to understand consciousness, reality, and the nature of life itself. The possibility of encountering extraterrestrial life, whether microbial organisms on Mars or intelligent civilizations in distant star systems, will add yet another layer of complexity to these philosophical questions. How would humanity react to the discovery of life elsewhere in the universe? What would it mean for our understanding of biology, evolution, and the nature of intelligence? Would we see ourselves as part of a larger cosmic community, or would we view extraterrestrial life as fundamentally separate from us? The discovery of intelligent extraterrestrial civilizations would raise profound ethical questions as well. How should we communicate with alien species that may have entirely different ways of thinking, perceiving reality, or understanding existence? What responsibilities would we have to protect and respect these civilizations? And how would we navigate potential conflicts over resources or territory? These questions will require not only scientific and technological expertise, but also careful consideration of ethics, diplomacy, and law. The development of interstellar communication technologies could be one way to bridge the gap between humanity and other civilizations. While we currently rely on radio waves to search for extraterrestrial signals, more advanced civilizations may communicate using technologies we have yet to discover, such as quantum communication or neutrino-based systems. Establishing contact with such civilizations would likely require entirely new forms of communication that transcend the limitations of human language and understanding. As humanity becomes more integrated into the cosmic fabric, we will also need to rethink our relationship with artificial intelligence, AI, and other advanced technologies. AI is already playing a key role in space exploration, from autonomous rovers on Mars to AI-powered satellites that monitor Earth's environment. In the future, AI could become even more deeply integrated into space missions, acting as co-pilots, mission planners, and even companions for astronauts on long-duration missions. AI systems could manage life support systems, conduct scientific research, and help ensure the safety and well-being of human settlers in space. The evolution of AI could also lead to the creation of entirely new forms of intelligence that exist alongside humans in space. These synthetic intelligences could operate independently or as part of human-AI hybrid systems, where human and machine minds work together to explore the universe. The rise of AI may challenge traditional notions of what it means to be human, as the distinction between biological and artificial intelligence becomes increasingly blurred. As AI systems become more autonomous and capable, they may develop their own goals, values, and forms of creativity, leading to the emergence of a new class of intelligent beings with whom humans must coexist. In addition to AI, the development of cybernetic enhancements and genetic engineering will likely play a key role in humanity's adaptation to space. Space is an inherently hostile environment, with extreme temperatures, radiation, and low gravity posing significant challenges to human biology. To survive and thrive in space over the long term, humans may need to enhance their bodies through genetic modifications that improve resistance to radiation, increase bone density in low-gravity environments, or even allow for hibernation during long space journeys. These modifications could fundamentally change what it means to be human, leading to the emergence of post-human or transhuman societies where biological limitations are transcended through technology. Future generations of spacefarers may have enhanced physical abilities, longer lifespans, or even the ability to integrate directly with machines through neural interfaces. This blending of biology and technology will create new ethical dilemmas as humanity grapples with questions about identity, individuality, and the definition of life itself. The idea of digital immortality, uploading human consciousness into digital systems, could further transform human existence. In this scenario, humans could transcend their biological forms entirely, existing as digital beings within virtual environments or as part of advanced AI systems. These digital humans could explore the farthest reaches of the universe without the constraints of physical bodies, interacting with other civilizations, conducting scientific research, and even experiencing reality in entirely new ways. The development of digital consciousness could also change the way we think about death and the afterlife. If human minds can be uploaded and preserved indefinitely, the concept of mortality may lose its significance, leading to new philosophical debates about the meaning of life and the nature of consciousness. Digital immortality could also enable humans to travel across vast distances in space by uploading their minds into spacecraft or communication networks, bypassing the limitations of physical travel and ensuring that humanity can explore even the most distant parts of the universe. As we expand into the cosmos and reshape our understanding of life, intelligence, and civilization, we will also need to ensure that our actions are guided by principles of sustainability and responsibility. The vastness of space offers seemingly limitless resources, but we must be careful not to repeat the mistakes of the past by exploiting these resources without regard for their long-term consequences. The preservation of planetary ecosystems, the protection of indigenous life forms, and the responsible use of space resources will be essential for ensuring that future generations can continue to explore and thrive in the universe. In the end, space exploration is not just about reaching new worlds. It is about expanding the horizons of human potential and reimagining what is possible. The universe is vast, full of mysteries and wonders that we have only begun to explore. As we push beyond the boundaries of Earth, we will encounter challenges and opportunities that will shape the future of humanity in ways we cannot yet imagine. The stars are waiting, and as we venture into the cosmos, we carry with us the hopes, dreams, and curiosity that have always driven us to explore the unknown. The future of space exploration promises to be a journey of discovery, not only of the universe around us, but also of the infinite possibilities within ourselves. The adventure is only just beginning, and the possibilities are as limitless as the universe itself. As humanity pushes deeper into the cosmos, the journey of exploration and discovery will evolve into something even more profound: the reshaping of human civilization itself. Our expansion into space will redefine what it means to be human, not only in terms of our technological capabilities, but in how we live, communicate, and interact with the universe. In this next phase, we are not just explorers but builders of new worlds, creators of new societies, and custodians of an entirely new chapter in the history of life. The leap from interplanetary species to an interstellar civilization will demand innovation on every front: science, ethics, culture, and governance. One of the most revolutionary developments in the coming era of space exploration will be terraforming, the process of transforming other planets to make them more Earth-like, allowing humans to live on them without the need for enclosed habitats. Mars, the Moon, and other celestial bodies offer tantalizing possibilities for this process. But terraforming will require immense scientific breakthroughs and technologies that, while still theoretical, are beginning to move toward practical exploration. On Mars, one of the key challenges is its thin atmosphere, which lacks sufficient pressure and warmth to support liquid water on the surface. Terraforming Mars would likely begin by increasing the planet's atmospheric pressure and temperature, possibly through the release of greenhouse gases. These gases could trap heat and gradually raise the temperature, melting the polar ice caps and releasing stored water and carbon dioxide into the atmosphere. Over centuries, this could lead to the formation of oceans, rivers, and even a breathable atmosphere. Scientists have proposed a range of strategies for this process, from manufacturing artificial greenhouse gases to using large-scale space mirrors to reflect sunlight onto the planet's surface. While the idea of terraforming has long been a staple of science fiction, its ethical implications are just as important as the technical challenges. Should humans attempt to transform other planets, especially if they contain microbial life? Would terraforming Mars, for instance, obliterate any indigenous life forms that might exist beneath its surface? These questions highlight the need for careful consideration of planetary protection, both in terms of preserving the natural conditions of other worlds and ensuring that humanity does not inadvertently cause ecological harm on a cosmic scale. Terraforming is not limited to planets like Mars. The moons of Jupiter and Saturn, such as Europa, Ganymede, and Titan, also offer potential for long-term human settlement. While these icy worlds are currently inhospitable, their subsurface oceans could one day be accessed, either by humans or by robots, for colonization or scientific research. These moons may never have atmospheres like Earth's, but they could host enclosed habitats or cities beneath their ice-covered oceans, where humans might live in close proximity to exotic, alien ecosystems. Titan, with its thick atmosphere and lakes of liquid methane, offers an especially unique opportunity, where future generations might develop technologies to adapt human life to a world so vastly different from Earth. As humans begin to terraform planets and settle moons, the question of post-Earth societies will become central to the future of space exploration. These new civilizations will not merely be Earth colonies. They will be distinct cultures that develop their own laws, social structures, and ways of life, reflecting the environments in which they live. A Martian civilization, for example, may develop a collective identity that is shaped by the challenges of living in a harsh, isolated world. Martians might value resourcefulness, resilience, and cooperation above all else, as survival on Mars will depend on careful management of resources and collaboration between settlers. Governance in these post-Earth societies will likely take forms that are different from those we are familiar with today. While early colonies may be governed by Earth-based nations or international coalitions, as populations grow and become more self-sufficient, the desire for autonomy will naturally increase. Martian settlers, for example, might demand the right to govern themselves, potentially leading to the creation of independent Martian states. These states could form alliances with Earth, the Moon, or other space settlements, but they may also choose to develop their own political systems that reflect the unique conditions of life in space. The need for new legal frameworks in space will also emerge as humanity expands its presence across the solar system. The existing Outer Space Treaty, which governs activities in space, prohibits nations from claiming sovereignty over celestial bodies and mandates that space should be used for peaceful purposes. However, as space settlements grow, this framework will need to evolve to address issues such as property rights, resource extraction, and interplanetary commerce. Who owns the resources mined from asteroids or the Moon? How will disputes between different colonies or nations be resolved? These are questions that will require the development of new laws, treaties, and systems of governance that balance the interests of different nations, corporations, and individuals in space. The establishment of post-Earth societies will not only change how we govern ourselves, but will also lead to the creation of new economic systems designed to support life in space. While Earth's economy is currently based on the exploitation of finite resources, space offers the potential for an economy of abundance. Asteroids, for example, contain vast quantities of metals and minerals that could fuel a space-based economy. Water, one of the most valuable resources in space, can be harvested from the Moon, Mars, or asteroids to support human settlements and to produce rocket fuel. As humanity moves toward a spacefaring economy, the extraction of resources from space will likely lead to the development of new industries and trade networks. These could include asteroid mining, lunar manufacturing, space-based energy production, and even tourism. The construction of space elevators, which would allow materials and people to be transported from Earth to space more efficiently, could revolutionize how we access the resources of space. Once established, space-based industries could operate with much greater efficiency than those on Earth, as the absence of gravity and the abundance of solar energy will reduce the costs of manufacturing and energy production. The development of a spacefaring economy will also give rise to new forms of wealth and power. Just as the Industrial Revolution reshaped global economies and societies, the exploitation of space resources could lead to the rise of new industries, corporations, and political powers. Companies that control access to valuable resources in space, such as rare metals from asteroids or energy from the sun, could become major players in the global economy. This shift will also raise important questions about equity and access. Who will benefit from the wealth of space, and how will these resources be shared or distributed among nations and individuals? One of the most exciting aspects of the future space economy is the potential for space tourism and the creation of space habitats that are not just utilitarian, but designed for human pleasure and exploration. Space hotels, orbital resorts, and even recreational space stations could offer people the chance to experience life in microgravity, to view Earth from orbit, or to explore the surfaces of the Moon or Mars. As space travel becomes more accessible, space tourism could become a major industry, generating revenue that helps fund further exploration and settlement. Space habitats designed for long-term human habitation will also evolve from the utilitarian designs of today's space stations to more complex and comfortable environments that support the needs of diverse populations. These habitats might include parks, cultural centers, and entertainment facilities, creating thriving communities that resemble the cities of Earth, but with the added thrill of being located on the Moon, Mars, or in deep space. The design of these habitats will need to account not only for the physical needs of humans, such as food, water, and air, but also for psychological and social needs, creating spaces that foster a sense of community and well-being. As we establish these new societies in space, the question of human evolution will become increasingly relevant. The human body has evolved over millions of years to thrive on Earth, but space presents an entirely different environment, one that is hostile to human biology. In low-gravity environments, bones weaken, muscles atrophy, and radiation exposure increases the risk of cancer. To overcome these challenges, future generations of spacefarers may need to undergo genetic modifications or use biotechnology to enhance their resilience to space environments. Genetic engineering could allow humans to develop traits that help them adapt to the conditions of different planets or space habitats. For example, Martians might be genetically modified to better withstand radiation or to metabolize oxygen more efficiently in the thin Martian atmosphere. These modifications could be passed down to future generations, leading to the emergence of a new, space-adapted human species. Over time, the physical and genetic differences between Earthlings and space dwellers could become pronounced, creating distinct subspecies of humans, each adapted to their specific environment. The development of cyborg technology could also play a key role in human adaptation to space. Future spacefarers might augment their bodies with artificial organs or limbs that enhance their ability to survive and thrive in space. For example, artificial lungs could allow humans to breathe in low-oxygen environments, while bionic eyes could enhance vision in the darkness of deep space. These enhancements could be integrated with AI systems, creating a hybrid form of intelligence that combines the strengths of human creativity and intuition with the processing power of machines. As we explore the possibilities of human enhancement, we will also need to consider the ethical implications of these technologies. Will genetic engineering and cybernetic enhancements create a divide between enhanced and non-enhanced humans? How will we ensure that these technologies are used responsibly and equitably? And what will it mean to be human in a world where our biology is no longer fixed, but malleable? In addition to genetic and technological enhancements, the development of digital consciousness could offer a radically different future for humanity. By uploading human minds into digital systems, we could transcend the limitations of the biological body and exist as digital beings, capable of exploring the universe without the constraints of physical travel. These digital humans could live in virtual worlds, interact with other forms of intelligence, or even control robotic avatars that operate in physical reality. The rise of digital consciousness would challenge our understanding of identity, individuality, and the nature of life itself. If human minds can exist indefinitely in digital form, what happens to the concept of mortality? Could multiple versions of the same consciousness exist simultaneously, and what would that mean for our sense of self? These questions will become increasingly relevant as we move toward a future where the line between biological and artificial life becomes ever more blurred. As humanity expands into the cosmos, the possibilities for exploration, discovery, and transformation are limitless. We are not just exploring new worlds, we are creating new ways of living, thinking, and being. The future of space exploration promises to be a journey of profound change, one that will shape the future of humanity for millennia to come. The universe is vast, and we are only just beginning to understand our place within it. As we push the boundaries of science, technology, and human potential, we are embarking on the greatest adventure in history, one that will take us to the farthest reaches of the cosmos and beyond. The stars are waiting, and the future is as boundless as the universe itself. The adventure continues, and the possibilities are truly infinite. As humanity advances further into the depths of space, the next frontier we face is not just the vastness of the cosmos, but the transformation of human existence itself. Each step we take away from Earth, every new technology we develop, and each discovery we make in the universe will gradually redefine what it means to be human and what our civilization can become. This future of space exploration will stretch beyond the physical expansion into space. It will spark revolutions in technology, biology, governance, culture, and even consciousness. The journey will be one of adaptation, reinvention, and boundless opportunity, ushering in an era of possibilities unlike anything we have known before. One of the key developments in this new phase will be the rise of artificial intelligence, AI, as a core part of human exploration and settlement in space. While AI already plays a significant role in space missions today, its future integration will be far more profound. AI will not only assist with tasks like navigation, system monitoring, and data analysis, but will become essential partners in the operation of entire space habitats, planetary bases, and interstellar vessels. These AI systems, equipped with advanced decision-making capabilities, will help manage life support systems, control resource distribution, and even make complex calculations required for long-duration space travel, all while adapting to the unpredictable nature of space environments. The collaboration between humans and AI could lead to the development of cybernetic societies in space, where human and machine intelligence work seamlessly together. In these societies, AI systems could take on many roles traditionally held by humans, including leadership and governance, while humans may focus on exploration, creativity, and decision-making in areas where human intuition is irreplaceable. Over time, this partnership may evolve into something even more integrated, as humans adopt cybernetic enhancements that merge biological and artificial intelligence. Neural interfaces that allow humans to directly interact with AI or control spacecraft with their minds could become commonplace, radically altering the relationship between humans and technology. This merging of human and machine could also play a crucial role in interstellar travel. Reaching other star systems, such as Alpha Centauri or beyond, remains one of the greatest challenges humanity faces, given the vast distances involved. While advanced propulsion systems like nuclear fusion, antimatter drives, or even the speculative warp drives are being explored, the journey between stars will still take decades, if not centuries, with current technology. However, the creation of cyborg explorers, humans augmented with advanced life support systems and enhanced longevity, could make interstellar missions more feasible. These enhanced humans could survive the harsh environments of space for extended periods, entering states of hibernation or slowing their metabolic processes to endure long voyages. But interstellar travel is not limited to the realm of biological beings. The concept of digital consciousness offers an even more radical possibility. In this scenario, human minds could be uploaded into digital formats and sent across space as information, traveling at the speed of light to distant star systems. Once they arrive, these digital beings could inhabit advanced robotic or synthetic bodies, effectively becoming post-biological explorers who can traverse the stars without the limitations of physical bodies. This would allow humanity to spread its presence across the galaxy in ways that are currently beyond our reach, transcending the constraints of time and distance that biological life imposes. While the technological and biological advancements of the future will push the boundaries of human potential, they will also pose significant ethical and philosophical challenges. As humanity evolves into a spacefaring species, we will be forced to confront deep questions about identity, individuality, and what it means to be human. The creation of digital consciousness, for example, challenges our understanding of the self, If a human mind can exist in multiple digital copies, is each copy a unique individual, or are they all the same person? And what happens when a digital version of a person diverges in experience and personality from its original biological self? These questions will also extend to the realm of artificial life forms. As AI systems become more advanced, the distinction between human and machine may begin to blur. In the future, it is possible that AI entities could develop consciousness or self-awareness, leading to the emergence of entirely new forms of life. These synthetic beings could evolve alongside humans, forming their own cultures, philosophies, and civilizations. This raises profound questions about the rights and status of artificial beings in human society. Will they be considered equals, with the same rights and freedoms as biological humans, or will they occupy a different place in the social hierarchy? And how will we navigate the potential for conflict or cooperation between humans and artificial intelligences in a shared interstellar future? The exploration of space will also necessitate new forms of governance and law that are adapted to the realities of life beyond Earth. While international treaties like the Outer Space Treaty currently govern space activities, the establishment of permanent colonies and space habitats will require more complex legal frameworks. As humans settle other planets, moons, and orbital habitats, the need for self-governance will become more urgent. These off-world societies will likely develop their own legal systems, political structures, and methods of conflict resolution, shaped by the unique challenges of life in space. For example, the scarcity of resources in space environments will require new approaches to resource management, ownership, and distribution. On Earth, water, food, and energy are abundant in many places, but in space, these resources will be tightly controlled and carefully rationed. This could lead to the development of post-scarcity economies, where technological advancements like asteroid mining, in-situ resource utilization, and advanced manufacturing systems ensure that basic needs are met for all inhabitants. In such societies, wealth and power may be defined not by the accumulation of material goods, but by access to information, technology, and creative expression. These spacefaring societies will also face the challenge of interplanetary relations. As human colonies on Mars, the Moon, and other celestial bodies gain independence from Earth, the dynamics between these worlds will evolve. Will Earth remain the central authority in the solar system, or will power become decentralized as new political entities emerge on Mars, the moons of Jupiter and Saturn, and in orbital space habitats? These new worlds may form alliances, trade networks, and even interplanetary federations, each with their own interests and agendas. Diplomatic relations between these worlds will require careful negotiation to ensure peace and cooperation in a potentially fractious and diverse solar system. The future of space exploration is also intertwined with the possibility of first contact with extraterrestrial civilizations. As we push further into the galaxy, the likelihood of encountering intelligent life increases. This could happen through the discovery of alien signals, the exploration of exoplanets, or even by meeting a technologically advanced civilization capable of interstellar travel. First contact would be one of the most significant events in human history, radically altering our understanding of life, intelligence, and our place in the universe. If we do encounter an alien civilization, the nature of the interaction will depend on many factors: technological disparity, communication barriers, and differing values or goals. These beings may be vastly more advanced than us, potentially viewing humanity in ways we cannot predict. Alternatively, we may encounter civilizations that are at a similar technological level, opening the possibility of cooperation or conflict. Establishing peaceful communication and understanding with an alien civilization will require a new kind of diplomacy, one that transcends human culture and language to bridge the gap between entirely different forms of life. The discovery of alien life, whether intelligent or microbial, will also force humanity to confront ethical questions about how we interact with the ecosystems and species we encounter. Should we terraform planets or moons that may host alien organisms, even if they are simple or microbial? What rights do these life forms have? And how should we balance our desire to colonize new worlds with the need to preserve and respect the life that already exists there? These questions will shape the future of planetary protection, a concept that seeks to prevent the contamination of other worlds with Earth-based life and to protect Earth from potential extraterrestrial contaminants. As we explore planets like Mars and the moons of the outer planets, ensuring that we do not inadvertently disrupt alien ecosystems or introduce harmful microbes to Earth will become increasingly important. This will require the development of advanced sterilization techniques, quarantine protocols, and ethical guidelines for interplanetary exploration. As humanity becomes more integrated into the fabric of the universe, the cultural and spiritual dimensions of space exploration will also expand. For millennia, humans have looked to the stars with a sense of wonder, using the cosmos as a canvas for myth, religion, and philosophical inquiry. As we begin to live among the stars, these traditions will evolve, leading to new forms of spirituality and philosophy that reflect our expanded understanding of the universe. Space itself may become a source of spiritual inspiration, as future generations contemplate the infinite vastness of the cosmos and their place within it. The experience of living on another planet, or traveling between stars, could give rise to entirely new belief systems, practices, and rituals that connect humanity to the universe in ways that transcend earthly traditions. Philosophers will grapple with questions of existence, consciousness, and the nature of reality in a universe that is far stranger and more complex than we ever imagined. In this future, art and creativity will also take on new forms. Space offers a unique environment for artistic expression, where the isolation, beauty, and mystery of the cosmos inspire new genres of music, literature, and visual art. Artists may draw inspiration from the alien landscapes of Mars, the swirling storms of Jupiter, or the serene emptiness of deep space. New forms of virtual reality and immersive experiences could allow people to explore the universe in ways that are both artistic and scientific, blending imagination with discovery. The fusion of technology and creativity will also lead to new forms of virtual worlds, where humans can experience alternate realities, explore distant planets, or even create entire simulated universes. These virtual environments could become spaces for artistic exploration, scientific research, or personal reflection, offering a limitless canvas for human creativity. As we venture further into the universe, the ultimate frontier we will face is not just the exploration of space, but the exploration of our own potential. The future of humanity in space promises to be a journey of transformation, one that challenges our understanding of life, intelligence, and the nature of existence. It is a journey that will take us to the farthest reaches of the cosmos and beyond, unlocking new possibilities for civilization, culture, and consciousness. The adventure is only just beginning, and the future holds boundless opportunities for discovery, innovation, and growth. As we continue to explore the universe, we are not only expanding our physical horizons, but also pushing the boundaries of what it means to be human. The stars are calling, and the next chapter of human history will be written among them. The possibilities are as infinite as the cosmos itself, and the journey ahead promises to be the greatest adventure in the history of our species.